So if I write this way, is it tilted or it is
No, no.
straight? It is
This
fine.
is straight. Yes,
This
it
is
is
straight
fine.
up. Oh, okay. Okay, let me know when you want to start.
Okay, okay. So I think it's a good point to start. Almost 40 people have joined the meeting. So before
All right.
the start, I would, sir, yeah, I would like to give a small introduction of Dr. Devasis Bora. I would like to request my colleague, the Secretary of Physics Academy of Northeast, Dr. Samrat De, to just give us a brief introduction to the participants. Samrat Da, are you there?
Yes. Um, I also welcome all the participants to this final day of the summer school. I hope it has been useful for all of you. Nevertheless, if there are some suggestions, we'll have a feedback session for you after the two talks. You can kindly share your feedbacks with us. And for this session, we are very happy to have Dr. Debashish Bora from IIT Guwahati here with us. Dr. Debashish Bora did his PhD from IIT Bombay, and then he joined Tezpur University as an assistant professor, and thereafter he moved to IIT Guwahati. Currently, he is an associate professor of physics in IIT Guwahati. He has done a lot of work in neutrino physics in beyond standard model. Actually, his academic accomplishments do not require any introduction, but I want to highlight the fact that he has been a very core member of PANE. So many things that we are having these days, Devashish Bora is one of the reasons for that. He is also the editor of PANE Journal of Physics. He is also a fellow of the Physics Academy of the Northeast. And he is most importantly involved in all the activities that PANE is doing. And I hope that he will also be there in future too. We are really happy to have Dr. Devashish Bora here with us. Thank you, Dr. Bora. Devashish, the platform is yours now.
Okay, thank you very much for the introduction. That was okay. So I hope you can hear me and see my screen and see my cursor moving, right? Hello?
Uh, Screen is not visible, sir, right now.
Oh, just one.
Did you share the screen? I think you stopped it.
Oh, it got stopped probably, I don't know. Okay. Uh, let me share again. Can you see now?
Yes, it is coming.
Okay, and you see the cursor moving, right?
Yes, yes. Yes, sir.
Okay. All right, good. So I was asked to talk about BSM physics. So it's BSM physics is a huge area. So I noted down some of the points like why BSM, but somehow the screen is a bit tilted, so I'll write it again. So first question we should ask like why we need BSM. Okay. So there are many reasons. So I'll not go into all of them, but you can actually divide these reasons into two categories. One is probably the theoretical one. So the standard model, I presume you have already got some idea from the previous instructors that it is a gauge theory of SU3 cross SU2 cross U1, and all the fundamental particles, that means the fermions, and their interactions mediated by gas bosons can be studied very nicely in the standard model. And we also know how the masses are generated through the Higgs mechanism. So everything is fits very nicely, but there are some issues, like one of the issues, like something called the hierarchy problem. So it is related to the fact that why Higgs mass is so light, 125 GeV. I mean, if you try to compute the Higgs mass, Higgs mass will get radiative corrections, and if there is no new physics scale between the standard model and the scale of gravity, the Higgs mass should be pushed to the scale of m Planck. Okay, so mh should actually go towards m Planck. So it is not radiatively stable. So we do not know why Higgs mass is so light compared to the known scale of gravity, which is the next new physics scale, which we think beyond the standard model. If there is no new physics between the standard model and the scale of gravity, for example, then there is something called flavor problem. The flavor issue is like you have seen that in the standard model, there are so many fermions. For example, you have top quark. The top quark mass is 173 GeV. The electron mass is like 0.5 MeV. So they are very different from each other. So that also is another puzzle, which we do not know why we have this kind of structures. Then we also can ask the question like why gravity is not included in the standard model. So we do not have a quantum theory of gravity. So that is another motivation to pursue beyond standard model physics theoretically. There can be many more, so let us not go into that far. So because of lack of time, I'm mostly interested in the experimental side. That there are some experimental hints also. Which tells you that there should be something beyond the standard model. So first is the neutrino mass. The neutrinos have mass. So in the standard model, neutrinos are massless. I will tell you why. Then you can talk about something called dark matter, which is there in this universe, but we do not know what kind of things can constitute dark matter. Then you can have another observation called the baryon asymmetry. That means the baryon sector in the universe is highly asymmetric. That is also another puzzle, which we do not know why it is so. We also have something called dark energy, which also plays a role in our universe, but we do not know what is the fundamental origin of dark energy. And you can actually keep adding to this list, but these are the most important ones in my opinion. So what we'll try to tell you some things about the first two or maybe three if time permits, and we'll tell you, like, I would like to tell you, like, why do we need BSM for this kind of scenarios, and how to construct BSM basically. So if you know that there is a problem in the standard model or the model that you are studying, how to proceed with to solving the problem from a model point of view, and how to test the model, or how to check that the model is fine from all other theoretical or experimental issues. All right. Okay, so let's start with neutrinos. So what do we know about neutrinos? Okay. So neutrinos, as you know, it is part of the, so if we go from the historical point of view, it was first proposed by Pauli from the conservation of energy in the double beta in the beta decay. So you know that if you count the number of electrons as a function of their kinetic energy, it gives you a continuous spectrum. So which is showing that it has to be a kind of a three-body type of process. If you take two-body, it will get just one point here. Electron will carry only one type of kinetic energy, which is coming from the mass difference between the. So, for example, this is a nucleus, which is going to A, Y, Z plus 1, emitting an electron. So if it is a two-body process, you will get only this line. But if it is a three-body, which is as proposed by Pauli, there will be a anti-neutrino here, and then the electron kinetic energy you cannot calculate exactly, so they will actually follow this a continuous spectrum. You can do permutation combination of the same process that will give you something called, like, for example, this one is called the usual beta decay. If you want to write it in terms of the nucleons, you can write it as neutron going to proton plus electron plus antineutrino. So this is called the usual beta decay, or you can say beta minus decay. You can also have something like nucleus going into another nucleus with one atomic number less, and that will emit a positron, and in that case it will emit a neutrino, and these are called B plus decay. So you can see that in every processes you have the lepton number conserved. For example, electron has lepton number 1, antineutrino has -1, and neutron and proton does not have lepton number. They have baryon number. So these processes actually conserve lepton number as well as baryon number. And if you have noticed in the standard model, you have seen that none of the processes actually the processes that you write at renormalizable level in the Lagrangian, which obeys your gauge symmetries, none of them actually violate lepton number or baryon number. And this is also another mystery, you can say, because we do not impose lepton number or baryon numbers as a symmetry in the standard model, but they emerge as some kind of accidental symmetries. Okay, so they have very interesting implications. You can also think of something called electron capture. So that is basically, so if you want to think of like proton plus electron. So the proton is part of some nucleus, it captures an electron and it goes into neutron plus electron. You can also think of inverse beta decay, where you have nu E bar plus proton going to N plus E plus. Okay, this is electron capture. This is inverse beta decay. So all these interactions play very important role in producing as well as detecting neutrinos in different experiments. For example, if you have, say, a water tank, and the water tank will have these protons, and if an antineutrino comes from somewhere, it can hit a proton and it can emit a very highly energetic. I mean, if your neutrinos are very highly energetic, it can also, like a GeV scale, it can also emit a GeV scale positron, and if the positron travels very fast inside your water detector, it can emit Cherenkov radiation, and that is kind of a blue light kind of things which comes in the detector, and that will be caught by your photomultiplier tubes, and that will be a very clear signature that an antineutrino has come and hit your proton and give you this kind of E plus. Okay. On the other hand, if you want to detect neutrinos, for example, if you look at this electron capture type process backward, you can think of like neutrino coming and hitting a nucleus and actually increasing the atomic number by 1. So that is how this, for example, the solar neutrino was discovered in a chlorine tank when the chlorine was being converted into argon by the solar neutrinos. All right, so this kind of things you will find in, I mean, almost all particle physics textbooks. So let us quickly go to the models. So if you look at the Lagrangian in the standard model, how do you write the standard model Lagrangian for neutrinos? So you will write the kinetic term. I hope you are familiar with these notations now. This is the electroweak gauge coupling. First one is the kinetic term, then the Lagrangian term, which gives you the interaction of neutrinos with the gauge boson, plus Hermitian conjugate. So here I'm writing the W plus and the nu bar L, so EL. So this L means we are talking about the doublet, which is the nu L and the EL. Okay. And if you write the covariant derivative of the kinetic term of this whole doublet, then if you decompose it in terms of the components, nu L and EL, you will get this kind of terms. So this is the charge current, and you all know that there is a neutral current also, which is given by G by 2 cos theta W, mu L bar, gamma mu, Z mu, nu L. Okay, so neutrinos have both charge current interactions with the charged leptons, and it can have its own interactions like neutrino, antineutrino, and Z interactions. And you also know that there at the tree level there is no interaction between neutrinos and photons, because obvious reason is that neutrinos do not have electromagnetic charge, so it doesn't couple to photons at tree level. So we are discussing only tree level interactions, and the theta W, as you know, this is the Weinberg angle, and it is given as G divided by root over G square plus G prime square, where G prime is the U1Y coupling and G is the SU2 gauge coupling. And they can be related to the charge as Z prime cos theta W as equal to E. Okay, so if you have any questions, please feel free to ask at any time. Now the question is how to, let's assume neutrinos have some mass, then see the implications. Now, before that, you know how the masses are written in the standard model. In the standard model, you have the Higgs, which is a SU2 doublet, and then you write, for example, L bar Y. So this is a Yukawa, and you write for example, if you have only the electrons, so if you write this kind of terms and the Hermitian conjugate. So as you know that once the Higgs gets a vacuum expectation value, which is V is equal to 246 GeV, you can write down the mass of the electron as Y V by root 2. So that will give you the electron mass, and V is 246 from the gauge boson masses and all, which are known, and the gauge couplings are known. So from that we can find out what is V. It is 246. So if you want electron mass to be 0.5, you have to tune your Yukawa coupling to say below 10 to the power minus 5 or so. Similarly, for other charged leptons as well as the quarks, you have to tune the Yukawa coupling appropriately, because V is always fixed to get the desired masses. Now this story fits perfectly well for all the charged fermion masses in the standard model. But if you want to do it for neutrinos, the usual puzzle is that the neutrinos, we do not have the right-handed neutrinos. So there is no nu R in the standard model, simply because we do not see nu R in any processes like the beta decays and all other things. Okay, so we know the parity violation experiments. So if you remember this textbook example of the cobalt nucleus decay, we know that the electrons come only in one particular directions, not in all possible directions. So that tells you that there is a parity violation. So that tells you that only one type of helicities are there for the particles which take part in the weak interactions. And even if the right-handed neutrinos are there. The problem is that it will be a complete singlet under the standard model because it is neutral. It does not have any SU2 or U1 interaction. So it's very hard to see this kind of particles in any experiments. Now, assume that there is some nu r, so you can write down the neutrino Yukawa also as say y nu L bar Higgs and nu r plus Hermitian conjugates. So this Higgs tilde, as you know, this Higgs tilde you also use when you write the mass of up and down type quark. In one of them, you have to use H tilde to make it SU2 invariant. So this is I polymetrics 2 and the conjugate of the Higgs field. So if you do that, you will find that so now I can write down my neutrino mass as because the Higgs will get value like 0 V by √2. So I can write the charged lepton mass as say Y L V by √2. And I can write down the neutrino mass as Y nu V by √2. So I have L and nu. So if you have seen the mass matrices of up and down type quark, so now this is the same story. What we have done is that we have hypothetically introduced this nu r into the standard model. So this is a new particle. So now I can write down the mass of the neutrinos and the charged leptons together. So now, if you want to go to the mass basis, so for example, I have already told you that these neutrinos and electrons take part in the charge current interactions, but those interactions are written in a for example, the way I write down here. So here these interactions are written in the flavor basis. So if you want to go to the mass basis, what you have to do, you have to diagonalize these mass matrices, which are coming here. So these are mass matrices written in the flavor basis because these are like, in general, these mass matrices are actually 3 cross 3. Both are 3 cross 3. This is very exactly analogous to the quark matrices. So now if I want to diagonalize it, so what we have to do, for example, we have to diagonalize this y nu. So y nu will be, say, u nu, y nu diagonal. Then we need one more matrix. We need two different matrices because this y actually is not Hermitian. It is not required to be Hermitian by the symmetry of the model. So that's why we need to have some kind of biunitary kind of transformation. Similarly, for the charged lepton also, we can write UL, YL diagonal, KL plus. So now what it tells you that you can actually go from the flavor basis to when you diagonalize it, you are basically in the mass basis because we have only 3 values in the mass matrices, the diagonal values, and that actually tells you that what are the masses of charged leptons, 3 charged leptons, electron, muon, and tau, and 3 neutrinos, nu1, nu2, and nu3. Okay, so if you do the same exercise like one does in case of quark, so that means I'm going from mu alpha, which is so this alpha means the flavor, electron, muon, and tau. So I'm going from this to mass basis like this. And similarly, right-handed ones, alpha r, I'm going to k nu I r. Similarly for E alpha L, this is electron, so the charged lepton of flavor alpha, it is going to UL EIL, and similarly E alpha R, charged lepton right-handed type flavor alpha is going to KL EIR. So if I do this transformation, I can actually write down or rewrite my charge current Lagrangian which I wrote earlier as I'm skipping the kinetic term. So this will be W mu plus. You remember here only the left-handed neutrinos and left-handed electrons take part. So I don't care about the right-handed ones. So that's why only the mass matrix U nu and UL will appear. K nu and KL will not appear here. So I will now go from the flavor to the mass basis. So I can write this as instead of nu alpha, I will write nu I now because I'm in the mass basis, and gamma mu, then U nu dagger, UL, and this will be IJ multiplied by EJL plus Hermitian conjugate. I can write down the neutral current also, but if you remember, neutral current has nu bar uh, and gamma mu, nu. So this is the same type, so it will have the U nu dagger. So U nus are unitary matrices, so they will cancel out. So there will no net U matrices appearing in the neutral current. So I can actually ignore the neutral current part. But here in the charge current, since one of them is neutrino and the other is the electron, so we get net combination of a matrix not which is not necessarily one, because the U nu dagger and UL is not necessarily equal to one because they are two different unitary matrices. So what is this matrix? So this matrix is nothing but something called PMNS matrix. So this is called U dagger PMNS. Okay, so from now on I'll just call it U dagger. So that means I can write down my charge current interaction as simply as G by √2 W mu plus mu I L bar U alpha I star E alpha L plus. So this U is very analogous to the CKM matrix. Okay, so you can recall what is VCKM in the quark sector. Okay, so people have now already discovered most of the elements about the UPMNS. CKM has been known for a long time, and so now what is the implication of this UPMNS? Let us take another look. So what is this UPMNS doing? For example, I can relate the flavor state of neutrino. So because I wrote the interactions earlier as for example nu E L bar gamma mu W mu plus EL. Okay, so that means in a charge current interactions, we always produce, for example, if the charge current interaction is initiated by electron, it will produce an electron type neutrino. Similarly, if it is initiated by a muon, it will produce a muon type neutrino. So they are always produced in a flavor basis, and even the generation wise quantum numbers are also conjure. For example, if you think about this electron type lepton number is also conserved. Muon type lepton number. So the lepton number is conserved in these interactions generation wise. So and that is how you get to know. For example, if you have a water tank and you are saying that some antineutrino has come and does some kind of inverse beta decay, how to know that antineutrino was electron type or muon type? Because electron type will always create a positron, and muon type antineutrino will always produce a positively charged muon, that means anti-muon, and they can be detected in the experiments. Okay, so from that we know that these flavors are always conserved. So now we have learned that we can write down the flavor state. For example, let's talk about like a flavor state that we like a quantum mechanical state of nu alpha. Now I can write this as this UPMNS, which I wrote as alpha j as nu j. Okay, so I can always write it. For example, here you can see this is one important thing which is true in the case of CKM also. So this only this combination U nu dagger UL, this is actually experimentally measurable because only this comes in as a combination. You will not be able to find out what is UL separately and what is U nu separately. Okay, so now you can always assume that UL is 1. That means your charged leptons are already in a diagonal basis. So all you are doing is actually you are diagonalizing only the neutrino matrix. Okay, so that's why you can always say that the PMNS matrix is nothing but the diagonalization of the neutrinos, given that the charged leptons are always diagonal, because only the effective combination of these two different unitary matrices actually appear in your uh, processes. Okay, so I can always write that neutrinos are diagonalized by their PMNS, not necessarily by the uni. So if I do that, if you assume the simple quantum mechanics, I can write down the I can put the space and time here. So this I can write as if you assume the plane wave solution, so this after some time it will actually because these are the stationary states or the eigenstates of the Hamiltonian. So that means you know how these new i's evolve with time. So that is the usual quantum mechanical time evolution of states, which we know from the solution of the Schrodinger equation assuming plane waves. So this I can write as U alpha j star e to the power minus I e j t plus I p j x nu j. Okay, so they will evolve like this. So now if we want to uh, find out that, okay, I create a neutrino of flavor, say, nu alpha. If I create a nu alpha, neutrinos, and let us say after it travels a distance x in time t, and you have, so this is like a source. So you in the source you create a neutrino of flavor alpha. It travels a distance x in time t, and you have a detector here, and the detector will actually try to find out what type of neutrino it is, again by its interactions with matter, whether it is producing an electron or a muon or a tau. That will tell you what is the flavor. So now let us say the in the detector you detect is not as a alpha, but you detect it as a nu beta. So then you can actually find out that what is the probability that a neutrino which is created at alpha as a alpha flavor after traveling a distance x in time t will actually convert itself into a beta type thing. So that one can find out just by the calculating the quantum mechanical probability, and that is basically your nu beta and nu alpha after traveling distance x in time t. So this I can write down as in terms of the PMNS and the mass eigenstates. So this will be U alpha j star, U beta k, then e to the power minus I e j t plus I p j x, and then nu k nu j. Okay, so and these two, as you know, these two are the states of the eigenstates of the Hamiltonian. So that means they are orthonormal. So they will give you a Kronecker delta. So that means you can write down k same as j. So this will give you u alpha j star, u beta j, e to the power minus I ejt plus I ejx. Okay. Now, since you found out this is the amplitude. So from this, you can also find out the probability. So in quantum mechanical probability, as you know, this is basically the amplitude squared. So this will give you nu beta, nu alpha, dx. This is square. So this, if you write down in terms of the UPMNS, this will give you alpha z, u beta j, u alpha k, u dagger beta k. And then this exponential part will also come, and that will be written as e to the power minus I e j minus e k t plus I p j minus p k x. So be careful about using the dummy indices. For example, in each of these term, for example, if you look at the this term, which is the amplitude already has a dummy index, which is j. So when you multiply two different amplitudes, choose the dummy index to be different. In one, you can choose j, and in the other, you choose k. If you choose the same dummy index, you will get a miscount. Okay. So if you do that, so now you can average over time. So if you average over time and do some more simplifications, you will be able to write that. I'm skipping some steps because these are very simple. You'll be able to work it out on your own. So if you and so average over time. So average over time means you integrate dt of this p alpha beta dx, and then choose a normalization constant such that your sum of the probability is 1. So I'm calculating p alpha beta as a function of x only now. Time I have averaged out. So n will be chosen in such a way that the sum of this is equal to 1, because the sum of probability has to be 1. So, and then you can also assume that mass is very, very less compared to the energy. And this we also know from the usual beta decay also, which was consistent with a massless neutrino compared to the energies involved in the beta decay processes. And so in that case, you can ignore some higher powers of, so for example, if you have this I pj minus pkx, this you can write as I ej square minus mj square minus ek square minus mk square x. So if you can actually Taylor expand this, you can take e out, and this will be 1 minus m square by e square, so that you can Taylor expand it. And then if you ignore higher powers of that m square by e square, then you will be able to write down this whole probability simply as p alpha beta x. You will be able to write this as u alpha j star, u beta j, u alpha k, u dagger beta k, exponential I mj square minus mk square divided by 2e. I'm assuming all the neutrinos to be moving in with the same energy, because they have different masses, but the mass is so small compared to the energy. That means I can ignore that that they have different energies. So E is the common energy, assuming M is very small compared to the energies. So now this is your probability expressions, okay? And you can see that this depends upon this mj square minus mk square. So one can take a very simple approximation that, okay, you have a two flavor. That means you take electron and muon only. So if you have two flavor, then your U matrix is the simple orthogonal matrix, cos theta, sin theta, minus sin theta, cos theta. So then you can write down this probability expression because you know each and every element of the U matrix. There's no phase here. I'll tell you why a phase when a phase appears. So now if you use this, you will be able to do this simplification and arrive at this probability expression. So that is homework for you. You can do that, not very difficult. So P alpha beta X will come out to be sine square 2 theta and sine square delta m square x by 4e. So this delta m square is basically m2 square minus m1 square. So this tells you that if you create neutrinos as alpha flavor, and if you assume there are only two types of neutrinos, so if that neutrino travels a distance x in vacuum, it can oscillate into another neutrino beta with this probability. Okay, and in general, you can write this p alpha beta as for a length L as delta alpha beta minus sine square 2 theta sine square delta m square L by 4e. So what it tells you that if your alpha and betas are same, that means electron. So this delta alpha beta will be 1. So this will give you the survival probability. That means if you talk about an electron type neutrino at at the source, after traveling, what is the probability that you will still detect it as an electron type neutrino? So that will be 1 minus sine square of these things. And if you ask like, okay, I create an electron type neutrino, what is the probability that I will detect it as a muon type? So that will be your delta. So then this Kronecker delta will be 0 because alpha betas are different. So then the probability will be just sine square theta and sine square delta m square L by 2. So these are the things people have, what people have seen in neutrino experiments is that neutrinos actually oscillate from one flavor to another flavor. And this was also known from earlier also, not even oscillation experiments, from the solar neutrino problem, atmospheric neutrino problem. When people measured how many neutrinos they are getting from the sun or even from the atmosphere, it actually fell short compared to what is expected. And later on, people realized that the common solution to this problem is basically neutrinos are oscillating from one flavor to another flavor. So since sun produces only electron type neutrinos, so if you count only electron type neutrinos in your experiment, you will always find a deficit because some of the electron type neutrinos are actually converting themselves or oscillating into the muon or tau type neutrinos when they are propagating from the sun to earth. So in neutrino physics, people have already calculated or discovered or experimentally measured these different mass score differences. So now this is a very simple expression for two flavor. Now you can also generalize it to three flavors. So that will be written in terms of different mass, different elements of the PMNS. Now for three flavor, you will have three angles, obviously, because it is a 3x3 unitary matrix, which you can think of as a complex version of 3x3 orthogonal matrix. Orthogonal matrix always has three angles, 3x3. It can, in principle, have, so you know that the 3x3 unitary matrix has 9 elements. So if you have three angles, 6 you can think of as phase, but what happens is that out of 6 phases, which can in principle be there, you can actually rotate 5 away because you're by redefinition of this charged leptons and neutrino, because there are 6 of them, 6 different charged leptons, 6 different neutrinos, and from them you can rotate 5 away. You cannot rotate all 6 away. That is a very simple exercise you can actually perform. It is also given in a book like Chang and Lee. So that tells you that you will have 3 angles plus 1 phase in the. So this is very similar to VCKM. Okay, and if you have So the phase is actually, if you have an n generation, so the number of phase has a nice formula. So this is n minus 1, n minus 2 divided by 2. So that's why I said if you have only two flavor, so you will put n equal to 2, so you'll see that the number of phase is actually 0. So if you have only two flavors, so there will not be any CP violation. So what do you mean by CP violation? So if you have non-zero phases, what will happen is that you calculate P alpha beta. That means, or say P electron mu. That means the probability of an electron type neutrino going to muon type neutrino. And this, if this comes out to be not equal to the probability of a anti-neutrino of electron type E bar going into anti-neutrino of muon type, if these two are not equal, that tells you that you have non-zero CP phase, non-zero CP phase. Okay, and currently we already have a hint that lepton sector's CP violation is actually non-zero. So, so this is all about vacuum. That means the neutrinos oscillate. Now you can understand that if neutrinos oscillate, it must have what it must have. It must have some mixing angle, because that is what you have seen in the formula here. So these are the essential things that you need some kind of mixing angle. That means it has some kind of non-trivial flavor structure, such that when you go from the flavor basis to the mass basis, you need to multiply with a matrix where this sine theta or theta is basically non-zero. So you need this. Also, you need the neutrinos to have masses. Not only masses, you need them to have non-degenerate masses. That means if all neutrinos have same mass, this term will also become zero, and it will not give you any oscillation probability. So this actually tells you two things, that it should have mixing and it should also have non-degenerate masses. So this is the problem where in the standard model, because in standard model you cannot write down the mass because we do not have the nu r. So here we have already introduced a nu r by hand, and that is actually one of the simplest BSM model you can construct. That okay, just like all other fermions have right-handed part, I will also add right-handed part, and that will give me neutrino masses. There's something more to that story I'll tell you later, but before that, just quickly summarize that if the neutrinos also travel in matter, what will happen is that it will interact with the protons and neutrons and electrons in the matter. So electron type neutrinos will, because all the interactions of protons and neutrons and electron, I told you when I discussed initially the beta decays and some permutation combination of the same beta decay process, which you can see that the electron type neutrino interact with them, electron type neutrino as well as antineutrinos. But muon and tau type neutrinos or antineutrinos do not have those effects. So that's why there's something called matter effect, which will play a role if the neutrinos actually propagate through matter. So there, the oscillation will be slightly complicated because you need to now, earlier you took the Hamiltonian to be a free particle Hamiltonian, just p square by 2m and so on. But now you have to take the effect of matter. So the electron type neutrinos or antineutrinos will actually see the presence of a different potential, which you can actually derive. I will not derive it today because it may consume more time. So this, you look at any particle physics books, you will find this derivation. So this derivation one can do just from the Fermi Lagrangian. So the Fermi Lagrangian is, as you know, this is GF. Why we are using Fermi Lagrangian? Because we are interested in the low energy kind of effective process. We are not at the scale of, say, electroic symmetry breaking like 100 GeV or like LSC energy. We are at a lower energy level. So if you are at a lower energy level, I can parameterize or write down all the electroic interactions as effective four Fermi interactions, and the four Fermi interactions, as you know, they are written as E bar gamma mu 1 minus gamma 5 nu E multiplied by mu E bar gamma mu 1 minus gamma 5 E. So I can write it like this. So if neutrinos are coming, and they will see the presence of electrons in matter. So this ZF is the Fermi constant, which I can write in terms of the electroweak gauge coupling divided by 4 root 2 MW, which is the W boson mass squared. That means once you integrate out all these massive gauge bosons, the low energy theory of weak interactions just looks like the Fermi theory, which Fermi proposed to explain the lifetime of neutron or beta decay processes. So if you do some more calculations, you will be able to show that this interaction actually gives rise to an effective Hamiltonian, which is given by H is equal to GF by root 2 number density of electron. Sorry, this is number density of electron and mu E bar gamma 0 1 minus gamma 5 mu E. So this you can further simplify, because 1 minus gamma 5 by 2 is gives you the PL. So this I can write as root 2 PF NE. So these neutrinos I can write as just left-handed ones now. These were written as a Dirac spinors. So I can write as, because this is how we write in the four Fermi interactions. So if you recall the four Fermi interactions, so here I'm writing everything as a Dirac spinor. Okay, that's why the 1 minus gamma 5 is explicitly put here. On the other hand, when I wrote the charge current interactions, so there I wrote everything as with a subscript L. That means there is all. So if you have a wild spinor with a subscript L, that I can write as a 1 minus gamma 5 by 2 Dirac spinor. Okay. So here I'm writing everything as a Dirac spinor. So that's why this 1 minus gamma 5 is explicitly put. So this I can write as now the left-handed ones only. So 1 0 new AL. So what this will do, so that means you have something called this potential, so charge current potential, which is root 2 GF by NE. So this is also known as the MSW potential, which is responsible for the MSW effect that we see in the neutron oscillations in the sun or any matter. So if you simplify this only for two flavor, once again, then it is then you can write down in two flavor. You can write down this potential as VCC 0 0 0. So this is actually important because I'm writing this in a basis of electron and muon. So that means this term is for EE. So the fact is that your matter in Earth or Sun, they have only electrons. So only the electron type neutrinos or antineutrinos are going to see some kind of matter effect or some kind of a potential. On the other hand, if you go to other types of neutrinos, they do not see anything. You can ask the question that they can still see, for example, if I have electron, if I have a say muon type neutrino, can they interact? They can always interact. They can interact through the neutral current interactions, right? We say this is Z. But the thing is that the neutral current interactions will be there in all diagonal terms, right? So if there is something which is coming everywhere in the diagonal term, which is always fixed, that will not contribute to your neutrino oscillation. So what you are looking at a term which is different for different flavor, because we have already seen that If you have something which is different for different flavor, that is only going to contribute to your neutrino oscillator. So you can add the neutral current potential also in the 1 and 2 term. They are actually a constant term added to both. Eventually, they will not contribute. So that's why we do not worry about the neutral current potential, which you can find out by the same approach. So if you use this now, because you know the form of the charge current potential, remember I forgot to tell you. So this Ne is the density of electron. So if the density of electron is 0, if you have a matter, there is no electron. So obviously there will not be any matter effect. Okay, so it is actually more the matter, more is the matter effect, which is obvious, right? So if you use this now, you do the calculation once again. What you will be able to find out, you'll be able to find out the neutrino oscillation probability. So you will find that the neutrino oscillation probability in two flavor will have the similar structure that I already told you earlier, but now the mixing angle. So if you do the two flavor oscillation in matter in the presence of this new potential, which will where only the electron type neutrinos will see this VCC, you will see that you have, if you want to find out the oscillation probability, which I told you earlier, this will be like sine square 2 theta, and then sine square, that term which tells you delta m square by delta m square L by 4E. Now, this will be not exactly sine square 2 theta, but sine square 2 theta effective now. And if you want to write the probability expression just like the one we calculated in the vacuum, you will find that this sine square 2 theta EF, which is not exactly the one that we have in the vacuum, but have the same structure. But this sine square 2 theta effective, you'll be able to write in terms of this charge current. So you can see, you will be able to find that this sine square 2 theta effective is something like delta sine 2 theta divided by square root of VCC minus delta cos 2 theta. This theta is the same angle as in the vacuum case, which is angle in the PMNS, plus delta square sine square 2 theta. All right, so that means your oscillation probability expression remains almost same, the structure, but the mixing angle, which is appearing as the first term, so that term actually is basically an effective term now, and this delta is your delta m21 square, that is m2 square minus m1 square divided by 2e. And VCC, as I mentioned already, this is square root 2 ZF Fermi constant multiplied by number density of electron. So now if if VCC is very, very small compared to your delta, then you can ignore this VCC term so that you can see that this is nothing but your 1. This is nothing but your theta effective is basically will correspond to theta. This will correspond to theta because VCC will ignore. So this will be like delta square cos square 2 theta, delta square sine square 2 theta. So that will give you just delta, and delta will cancel out. So this is ultimately sine square 2 theta, which is same as the vacuum expression. Now, if you have, so this is the vacuum case. That means your matter potential is so small that it is not causing any change in your neutrino oscillation probability, and you are getting the same result as you have already seen in case of vacuum. On the other hand, if you have VCC, which is much large compared to delta, then what will happen is a VCC term will dominate. If you can see the expression, VCC will be so large compared to the delta, then the sine 2 theta effective will become almost 0. That means theta effective will be almost 0. So that means the oscillation is very small, small. But what is interesting is that if you look at this expression, there is a possibility that you will get maximum maximum mixing. You can have maximum mixing when this VCC minus delta cos 2 theta term is equal to 0. What will happen? Then this term will be 0, and then we will have delta sine 2 theta and divided by delta sine 2 theta. That means you will get a maximum sine 2 theta, which is going into your oscillation probability. So that is very interesting because that gives you a maximum oscillation probability. So VCC is equal to delta cos 2 theta. So this tells you that sine square 2 theta effective is equal to 1. Okay, so that gives you maximum oscillation probability. So maximum oscillation. And this is actually known as the MSW resonance. Okay, and since so this is what, so this can happen. So if your VCC is positive, so VCC is root 2 ZF and E. So this is positive. Number density ZF is a positive number, and this we are equating to delta cos 2 theta. Cos 2 theta is positive, so that tells you that this delta has to be positive. So that means that delta has to be positive. So this tells you that delta M21 square is positive. So which tells you that M2 is greater than M1. Of course, this analysis we have done only in 2-flavor case, but even if you extend it to 3-flavor case, you will see that this result actually does not change. Okay, so this brings me to the now let's come to what we know about the neutrino oscillation data from the experiments, and now for that we have to go to 3-flavor, and we have not done the derivation for 3-flavor, but you can do it simply by extending the mass matrix structures and all. So for the 3-flavor, you can look at this particle data group. They update the data every year by using the latest experimental data and the statistical analysis. So there you will find what is the mass squared values. So this will be around 7 into, I will write the values which I quoted from 2016. They keep changing slightly, but not much. So 7.37 into 10 to the power minus 5 electron volt square. Delta M3L square is 2.5 into 10 to the power minus 3 electron volt square. So this L can be this L can be 1. You can write L is 1 also, it's not a problem. So that, but the point is that if you write L equal to 1, why this mod square is written? Because we do not know the sign of this term. I'll tell you what is the implication of this. So what does it mean is that if you, so this tells you that we do not know whether M3 is more than 1 or M3 is less than 1. So that means I have two possibilities. I have the possibility like M1 less than M2 less than M3. I also have the possibility like M3 less than M1 less than M2. Okay, so this is called the normal hierarchy, and this is called the inverted hierarchy. But in both the cases, you notice that I always put M1 less than M2, and this is because of the result that I mentioned from the MSW resonance in the sun. because when we calculate the solar neutrinos, it has also gone through the matter effect inside the sun. And if we compare the experimental results with the number of neutrinos produced in the sun, going through the matter, going through the vacuum, everything we have to take into account. And that matches with our uh, experimental data. And from the solar neutrino or the MSW resonance, I told you that we know that M2 is actually more than M1. So M2 is always more than M1, but M3 we do not know whether it will fit at the bottom or it will fit at the up. So that's why this sign is, so that's why we write only the absolute value of this quantity. And this is called atmospheric mixing angle. And on the other hand, the delta M21 square is the solar mixing angle, which is 10 to the minus 5. So these two are known. On the other hand, we do not know what is the, so that's why since we know only the two mass square differences, we still do not know the lightest neutrino mass. So the lightest neutrino mass is not known. That means M lightest. I'm calling M lightest. I'm not calling is at M1, for example, because M lightest can be either M1 or M3, depending on which hierarchy we're talking about. M lightest is not known. Okay, so this is one thing. It can be, but it doesn't mean that M lightest can be anything. Okay, it has to be small still because we have some indirect hint. I will tell you. So what else we know? We know the mixing angles. So sine square theta 1, 2 around 0.29. Sine square theta 2, 3. This is around point. It depends on the hierarchy. If it is normal hierarchy, it is 0.43 for normal, and it is 0.56 for IH. If we talk about the last angle, sine square theta 1, 3, this is 0, 2. This is very small. In fact, before 2012, people thought that sine square theta 1, 3 is actually 0. So that actually led to many model building in neutrino physics based on some mu tau symmetry and so on, because they actually predict theta 1, 3 to be 0. But after 2012, because people have discovered in different experiments, like Diabe, Double Show, Renault, and so on, that theta 1, 3 is actually not 0. It is small compared to the other ones, but it is not 0. So that has actually changed the model building, kind of BSM model building for neutrino physics to some extent, because now we have to take care of the non-zero theta 1, 3 as well. Okay. So this is another thing. So if you compare with the VCKM, in the VCKM, the angles are not this large. So the angles are small relatively compared to the neutrinos, and masses are of course very different. So here the masses are close to each other. Like you can see that the mass differences are like 10 to the power minus 5 electron volt square, 10 to the minus 3 electron volt square. So they are relatively close to each other, and the angles are large compared to VCKM. So that is like people do different BSM model to explain like, okay, why if you have the same type of if you have a model to explain why the quark mixing is small, why the neutrino mixing is large, so you can actually think about different ways to do that by either by incorporating some kind of symmetries, discrete symmetries, continuous symmetries, and so on and so forth. So there are lots of model building things people do. So I don't have much time for the first lecture, so I will just tell you a few more things about neutrinos. For example, I told you that the lightest neutrino mass is not known, but it doesn't mean that you can take any neutrino masses, because that will play a role in the beta decay spectrum. For example, if you look at the the absolute mass of neutrino. We know only the mass square differences. So the absolute mass of neutrino, you can find out from the beta decay once again. So if you look at the beta decay spectrum, differential distribution of the number of electrons is the energy of the electron. if you plot as a function of the electron energy, you will find that this looks like this will fall like this. Okay, and if this is for, say, neutrino mass 0, if the neutrino mass is non-zero, so it will fall at a different rate towards the end of the tail. Okay, so this line is for m nu not equal to 0. Okay, so this is not very difficult to understand. You can look at the kinematics of the beta decay, just do the energy momentum conservation, and from that you will be able to find out that this is given. I mean, if you want, you can look at the book by Crane. You look at Crane, the chapter on beta decay. It's very beautifully explained how the neutrino mass, non-zero or zero, can play a role towards the end point of your beta decay distribution by changing the slope at which it is actually going to zero. So from this, but you need very highly sensitive experiments to actually distinguish, because see, neutrino masses are of sub-electron volt. On the other hand, these energies are of the order of kilo electron volt. Okay, even if you look at the tritium beta decay, where these energies are relatively small compared to the other heavier nucleus. So there are experiments where people are looking at it. So they mostly use tritium because uh, you can have better resolution. So for the tritium, this is tritium of isotope of hydrogen is going into 3 helium plus electron plus antineutrino. And the term which is important for the endpoint, it is actually written as the effective neutrino mass, which is given as m nu summation of u e I whole square m I square. So this has to be, so this actually plays a role. So this is what n nu I mean. This is the effective mass. So this is less than 1.1 electron volt. So as you can see that this bound is slightly weaker compared to the scale that we have from the neutron oscillation experiment. But mind you, neutron oscillation experiments cannot tell you the absolute masses. It can only tell you the mass score differences. But it doesn't mean that you can take very high values of neutrino masses, but just keep their mass differences small, because from the other experiments like the beta decay and so on, you know that the neutrinos cannot have too large mass, because otherwise you would have seen its effect when the neutron decays into proton plus electron plus antineutrino. On the other hand, if you look at cosmology, cosmology gives you an upper bound, and that is given as the sum of the absolute neutrino masses. And that, as of now, this is 0.12 electron volt. So this is from the Planck experiment, and this is 2018 data. This is rather large, rather strong compared to your laboratory experiments. Like so, this bound is from the Catherine experiment, which is in Germany. Okay, so this is about the neutrinos, what we know about neutrinos so far. So we also have, as I mentioned, there is a phase in the leptonic CP phase, and right now we have some evidence that it is non-zero, which is a good sign, because then we have some CP violation. It can have some implications. Now coming to the neutrino mass in next few minutes that I have. So what do we know about? So I already assume neutrinos to have mass, because I wanted to have it mass so that I can explain the oscillation, because now we have realized that neutrino oscillation tells you that it has masses. Now I already mentioned one possibility, which is I mentioned Dirac mass. That means I treated the neutrinos to be exactly same as the other fermions. So that's why I wrote as L bar H tilde nu R plus Hermitian conjugate. And this gives me a mass like MD nu L bar nu R plus Hermitian conjugate. So that means I can write down this whole thing as just MD nu bar nu, where nu is the Dirac minor, which is nu L plus nu R. Okay. So is there any problem with this? There is no problem as such. This is fine, but this actually raises two important things. One is that this Yukawa that you have taken, because you know that your V is 246 GeV. So that tells you that if you want sub-electron volt neutrino mass, that tells you that Y has to be less than 10 to the power minus 12. Okay, so this is very fine-tuned, which is not considered very nice in any theoretical setup. So if you have very small dimensionless numbers in your theory, you better have some reason why it is so fine-tuned, especially when other Yukawa couplings in the standard model are not this fine-tuned. So this is one thing. The other thing one can ask is that this new R is actually a singlet under the standard model. So why can't we write a bare mass term for the new R? So we can write the mass term for new R also. So that brings us to the conventional seesaw model. So for example, so then I have to talk about something called Majorana. So the Majorana probably you have not studied in the standard model, because in the standard model we do not have any Majorana fermion. So what Majorana fermion means? Majorana fermions means that the particle is its own antiparticle, right? So, and in the standard model, if you talk about the electron or charge fermions, they cannot be their own antiparticle because they have electromagnetic charge, and you know that electromagnetic charge is conserved. But for neutrino, it is a special case because neutrinos are neutral. They do not have any electromagnetic charge. So you can have neutrinos as a Majorana fermion. So in that case, you can write down the Majorana mass for neutrinos. So the one easiest way, which was proposed by Weinberg, is that you have the Higgs. You can write down Higgs and then L bar C. Then you can write L and then again another Higgs. So this is a dimension 5 operator, which has to be suppressed by a cutoff scale. So this is called the Weinberg operator. Weinberg operator. So you must have already noticed when you learn the standard model that we write all the terms as dimension 4 terms, because your Lagrangian is Lagrangian density d4x. So that means if your Lagrangian is dimensionless, that means your Lagrangian density should have mass dimension 4, because we live in 4 space-time dimensions. But you can always write higher dimensional terms, but then you have to like suppress it by some kind of dimension full coefficients. Usually we do not write these terms because if you look at the power counting, these terms are called non-renormalizable, because and what it means is that if you take radiative corrections, they actually diverge, okay? And they tend to infinities, so which we do not like. So usually we do not write it, but if we do not worry about the physics above this lambda, which is the cutoff scale, if you only focus on the low energy effective theories, like we talk about Fermi theory as a low energy theory of the standard model to understand weak interactions. If you are agnostic about physics above a particular scale, that means you already put a cutoff in your theory like a lambda. This is fine. So what it tells you, so this Weinberg operator is very nice because it gives you a Majorana mass. So this tells you that you can have a Majorana mass of neutrinos, which is basically the Higgs wave squared, which is V squared by lambda. And if V is 246, you know that lambda has to be like more than, I think, 10 to the power 14 more GeV. So this gives you an interesting idea. That means that if your electric scale is say 246 GeV, but if you have a cutoff which is like this large, then you can get a light neutrino mass of sub-electron volt. Okay. And this actually gives you some idea like what kind of model you can have to actually generalize this Weinberg operator, because this is a non-renormalizable operator, because here we have not introduced any new particles. But if you introduce new particles, you can actually write down, or you can get this kind of Weinberg operator from a renormalizable theory. Now, what kind of theories you can have, so that actually tells you what kind of models you can have. So, and that comes very naturally, very nicely in the sense that, for example, you know that H is a doublet. This is also a doublet under the standard model. And from the group theory, you know that if you multiply for SU2, if you have 2, which is the fundamental, 2 cross 2, it gives you 3 plus 1. Okay, and this is very easy to understand because they follow the usual angular momentum addition that you already know from the quantum mechanics. Okay, so that means if I want LH operator to write in terms of the in terms of some renormalizable interactions, I can either use a singlet under the standard model, or I can use a triplet under the standard model. So that actually tells you how to write down seesaw models of neutrino masses. So seesaw models actually try to find out renormalizable theories which can give you the Weinberg operator at low scale. Okay, so that is the meaning. So for example, what LLHH, so the Weinberg operator tells you that you have this neutrino, and you have this another neutrino, and then you have this Higgs. Okay, so these are something called vacuum insertion. They are not like a final state, so that's why you put a cross here. You put a cross here because they get a vacuum expectation value, so they are not necessarily like a 2-to-2 process. So this is like the 2-point correlation function of Majorana fermions, and you can see both the arrows are coming in the same direction. So that is because you have written Majorana terms, and since they are its own antiparticle, so you can write this term. But if you write it for Dirac fermion like electron, you cannot write both the arrows going in the same direction. You have to write the arrows moving in only one particular direction because you have to obey the charge conservation. But here it is not required because neutrinos are Majorana fermion. So this is the Weinberg operator, which I mentioned. Now, if you want to use this 2 cross 2 is equal to 3 plus 1 type of group theory idea, you can actually try to decompose it in different ways. So, for example, the easiest way is like you have this neutrino, nu L. You have another one coming from this direction, nu L. And you don't want to write this kind of dimension 5 operator. You want to write only dimension 4 operators. So that means if I put a Higgs now here, which is the vacuum expectation value of this, I can put a vacuum expectation value of Higgs again here. So I don't want to join these 2 points together because that will give you the usual Weinberg operator, which is dimension 5. I want to write dimension 4. So that means I will join these 2 points. And this I can do by using a right-handed neutrino, which is singlet. Okay, so what it means, so if I now talk about the low energy version of this theory, that means I will consider this nu to be very heavy, and nu have mass, say, mr. So what I can do, I can write down, so this Yukawa is, say, y. Okay, this Yukawa interaction. So this will actually lead you to something like y h y h divided by m r at low energy, which is very similar to the structure of the Weinberg operator, because Weinberg operator gives you Higgs square divided by lambda. So now lambda is basically coming from these heavy right-handed neutrinos. So what it tells you that if you introduce heavy fermions like MR or the nu R, if these are heavy because they can have a bare mass term, so they will give you light neutrino mass because of the different size of this electroic scale compared to these heavy fermion scales. So that is basically your, this is called seesaw. Because if you make MR very heavy, nu R, then means your nu L becomes very light. Okay, so this is like a usual seesaw that you have. So this is not the only way. You can also have, as I mentioned, 2 cross 2 is equal to 3 plus 1. So you can think of this, you can also replace this nu R as something called triplet. So this is called type 1 seesaw. Type 1, where you have only right-handed neutrinos of which are singlet, but you can have triplet also, which is triplet under the electroweak or the SU2, but it has 0 charge under U1Y. So that will give you your type. So this is called type 3. You can also have type 2, and the type 2 is slightly different. So that brings you a new scalar. So you have this nu L, and you have this nu L. So they can directly couple to a scalar, which is called delta, and this is a triplet under the SU2, and they have hypercharge 1. I'm assuming that your lepton doublet has structure like 2 and mm, hypercharge, if hypercharge minus half, then this should be minus 1. Okay. And how to get the Weinberg type operator? Because then you can write this as this is your Higgs once again. And this is coming because you can write down this delta Higgs term in your Lagrangian, and you can also write delta LL term in the Lagrangian. Both terms you can write. So this is the scalar potential term, which will have a mu, and this is a Yukawa. So what does it tell you? It tells you that if you, because you will have this term, plus you will have m delta square term. Of course, there will be conjugates and all. I am ignoring them for the moment. So what does it tell you? So if you actually, so this is like your potential. So if you take the del V by del delta, it actually gives you a term like m delta square delta plus mu Higgs square. And if you minimize the potential, so this will give you 0. And then if you find out what is your delta, that is the vacuum expectation value of this actually gives you minus mu Higgs square divided by m delta square. So once again, if I write down the neutrino mass coming from this, I will write as y multiplied by the vacuum expectation value of delta, which is again mu h square divided by m delta square. So here also you can see that if m delta is very large compared to the Higgs, you can get a seesaw. So in all the 3 models of the seesaw, you can see that the structure of the model actually tells you naturally why the neutrino mass is so small compared to the electroic scale. It is just because you have introduced some heavy degrees of freedom, either in the form of a triplet scalar, triplet fermion, or a singlet fermion, such that when you write down the neutrino masses at low energy, it comes out as an effective combination of the electroic scale square in the numerator divided by a heavy scale in the denominator, and that actually tells you the how the neutrino masses are generated. So these seesaw models are usually the tells you that neutrinos are Majorana. One can also try to probe. So how to know that neutrinos are Dirac or Majorana? So that is another important question, which we still do not know. So that this canonical seesaw models predict that the neutrinos are Majorana. But neutrinos can be Dirac also. We do not know. So how to probe these things? So the how to probe this thing is something called neutrinoless double beta decay. So that is a process like heavy nucleus where the down type quark goes to up type quark. Down type quark goes to up type quark, and this is your W, and this is electron W. So if neutrinos are Majorana particle, you can think that the neutrinos can, because you can write the same the arrows moving in the opposite direction here, because neutrinos are its own antibody. You can think of like one virtual neutrino coming and eating another virtual neutrino, because they are its own antiparticle. Okay, and since they are virtual, you do not have to conserve energy or something, so that you don't have to emit anything extra, because they are anyway virtual fermions. So this is possible only when neutrinos are its own antiparticle. So that means you will see some kind of processes where a heavy nucleus, so D, you can think of this is like a neutron. Neutron is converting into a proton. So you can think of like some nucleus, which is A, X, Z, is actually going into A, Y, Z plus 2 uh, plus 2 electron with no neutrinos in final states. We already have this kind of processes, but with two anti-neutrinos in final. So they are called the usual double beta decay. But if you see this kind of process also where there is no neutrinos in the final state, by the way, how do you know there is neutrino or there is no anti-neutrino? That they will be able to find out by the energy distribution of the electrons. Because if it is a two-body process, or if it's a three-body process, or it's a four-body process, the distribution of the electrons will be different. So far, we have not seen this process, which is called the neutrinoless double beta decay. But if we see this process, it will verify that neutrinos are actually Majorana fermion. And this process actually, if you calculate the amplitude of this process, it is not very difficult. So the amplitude of this process goes is proportional to ZF square and U EI. This is the usual PMNS matrix. Then the mass of the neutrinos divided by this momentum transfer Q square, and the other some gamma mu something coming. So I'll not talk about this. Let's, because I'm running out of time. So this is basically governed by this term. And basically GF is already known, so there's nothing new about it, but you can write down in terms of the masses. So it's here, as you can see, that the amplitude of this process is proportional to the neutrino mass. So that's why if neutrinos have a Majorana mass, then only this amplitude of this process will be non-zero. All right, so there are many other things to tell about whether the neutrinos are Majorana or Dirac. So I will probably stop here, and because I think I'm already running out of time. So if you have any questions, I can answer, and then we'll probably take a break.
So why one cannot measure the direct mass of the neutrino from this double beta decay? No, sorry, single beta decay process.
Yeah, we can measure. As I mentioned, we can measure the upper. So from this kind of processes, we can measure it. So right now we have an upper bound of this 1.1 electron volt from the tail of the beta decay, and this Catherine is planning to reach sensitivity of, I think, 0.5 electron volt. But this is very hard. So you can see that the 0.5 is still much weaker compared to the bound we have from cosmology, for example.
So participants, anything else you want to ask? Query, questions, comments? You can unmute yourself.
Hello, sir.
Yes.
So you have mentioned that in 2x2 representation, it either it can have a triplet or a singlet representation. And from this, we can get a hint about the seesaw model. So can you please explain again? I am a bit confused.
Oh, yeah. I mean, if you have 2 cross 2 is equal to 3 plus 1, so that means if you look at the Weinberg operator, so this is like a multiplication of 2 with 2. So that means H and L, if you combine together, you can actually connect it to either a singlet particle or a triplet particle. Similarly, if you think of this LC and L, they are also 2 and 2. So if that 2 cross 2, you can combine to either a singlet or a triplet. So that's why here, if you see, this is basically L. So L and H. So L and H, they are 2 cross 2. So I am actually connecting it to a singlet. Okay. So because 2 cross 2 will have a singlet, 2 cross 2 will have a singlet also, and plus a triplet also. Now I am taking this singlet out and multiplying it with a, say, new R, which is also a singlet. And 1 cross 1 is always singlet. Any term that we write in the Lagrangian, that has to be singlet under the group transformation, right? So that means I can write it like this. But if I now use a triplet, what I'm doing is that I'm taking the, and because 1 and 3 are different, right? 1 is the antisymmetric combination of 2 triplet, and 3 is the symmetric part of the two triplet. So now, sorry. Now if I take the triplet, which is sigma R, you can now see that I'm taking this triplet. So that means I will take this 3 part out of this 2 cross 2, which is the L and Higgs, and I will multiply this with a triplet, which is the sigma R. Now this 3 cross 3. Now 3 cross 3 will also give you a singlet. So the 3 cross 3 will give you 1 plus 3 plus 5. And that is the same as the quantum mechanics, this angular momentum addition algebra. Because 3 is basically the 2j plus 1 if you think. So 3 is basically 1. The spin value 1. So if you multiply 1 plus 1, 1 plus 1 will give you 2 plus 1 plus 0. And 2 is basically, if you again think of 2j plus 1, so 2 will give you 5, and 1 will give you 3, and 0 will give you 1. So this 3 cross 3. So that's why the this group algebra is very simple for SU2, because it just follows the angular momentum algebra. So this is giving you 5 plus 3 plus 1. Okay, so that means when I multiply this 3 of this 2 cross 2 with another 3, which is triplet, I will again take this 1 out of the whole thing, because the final term that I write in the Lagrangian has to be singlet. So this is how one can construct, I mean, this kind of models.
Okay, sir. Thank you.
Hi, Devasija.
Oh, hi.
Hi. So, you will be taking the other session after some time?
Yeah, that is the plan, right? What you have
Okay.
a break of
Yes, yes.
15 minutes, right?
Yes,
Or how
yes.
much time
I
we
think
have?
that's better. Yes.
I mean,
You
next
can.
class, probably I can take 1 hour, not more than that.
Yes, yes,
Because
yes.
otherwise, if this, I think I overshoot a bit slightly.
Yeah, no, that's okay, fine. Yes.
That's fine, no? Okay.
Yes, 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 yes. So if there is no question, then we can take the break and come back after 15 minutes.
So what
Yeah.
time we should come back? 5.
At
Here it is
5 is,
5:10.
I think it is, yeah. So after it is 4:40, let's take a 20-minute break and start at 5.
5 p.m. Okay, yeah, okay.
Yeah, okay.
That's fine. Yeah,
So
okay.
please, everyone, you please join up at 5 o'clock. Yeah. Okay, yeah.
Bye bye.
Okay.
Hi, Devasja.
Yes.
Yes, we can start now.
Okay.
So I have informed all the participants in the group to join. So they will be
Okay.
joining. In the
Okay.
meantime, you can start. Yes, yes.
Okay. Yeah.
Yeah.
Okay. So in the last class we discussed neutrinos. So we tried to revise the neutrino interaction in the standard model and neutrino oscillations, what we know about neutrinos so far, and how to get neutrino masses in the canonical seesaw models. But that is not the only thing about neutrinos. There are many other things, like there can be many different types of models and many different types of phenomenology of those models as well as neutrinos. So since we don't have much time, so I'm just moving on to another topic, which is related to dark matter. That is also one of the evidence of the BSM physics. So what we know about dark matter. But at the end, I can take questions both on neutrinos as well as dark matter, whatever you have. So dark matter is something which we know it's there in the universe, but we do not know what is actually made up to dark matter. So for example, if you look at the current distribution of the energy density in the universe, so only around this is the visible matter, which is around 5%, and then around 27%. So this is your dark matter, 27%. And then the rest of is 68% is dark energy. So for the moment, I will focus only on dark matter. So we knew about dark matter for a long time. So what are the evidences? Just quickly go through the evidences. So there are evidences from both astrophysics as well as cosmology. So the astrophysical evidences came long time ago. So if you look, for example, we know that we live in a galaxy like Milky Way, let's say, Milky Way, and this is, say, the galactic center. Most of the masses will be located near the galactic center. And if you go away and away, so if you look at any object here, let us say, which is at a distance, say, r, you can find out its acceleration, which is v square at a position r divided by r. You can also find out a as g m by r. M is the mass of the galaxy, which is enclosed in the radius r. Okay, and we know that the mass, if the galaxy has a uniform density, and if we assume, for simplicity, let us assume the galaxy to be a spherical one, although most galaxies are not completely spherical, they have a kind of a disk kind of shape. But assuming it to be a spherical, I can write down the mass to be 4 by 3 pi r cube rho. Okay. So then I can use these relations of the acceleration and find out that for small r, I can write down this v square r by r is equal to g by r square. Oh, sorry, this one has to be r square, 4 by 3 pi r cube. So this tells you that v r is proportional to r for small r's. That means your mass is still proportional to r cube because rho is constant. But for large r, if you go to large r, that means you go completely outside the visible radius of the galaxy. So if you take r here, let us say, so then what will happen? Your mass is basically fixed. So mass is not increasing beyond this one, because the galaxy has a particular size which you can see just by the optical telescope, because all the stars will be concentrated only up to this region. But now if you are talking about something which is very far away, and if you look at its acceleration, so you can write down your for large r, you can write you can find that your m is mostly constant now. M is not increasing as r cube because you are going beyond the visible radius of the galaxy. Then you can use this relation. So you can find that your v is going as 1 by square root of r, because in that case you will not write so this is 4 by 3, so there will be a row also. So you will not write this thing as r cube, you'll just write this whole thing as m here. So then this is v square and this is r square. So this r and r will cancel out. So this is like v square is proportional to 1 by r. So that's what v is actually proportional to 1 by root r. So this is what we expect from Newtonian gravity, that if we are looking at some object like a gas cloud or some kind of star which is far away from the galaxy or maybe inside the galaxy, if we look at the velocity of those objects, we will see this kind of behavior, that v will be proportional to r at small scales, and v will go as 1 by square root of r if we go to large scale. So that means we can plot this v as a function of r, and it should grow initially and then it should fall. Okay, so, but what we have observed is that it remains more or less flat. Okay, so this is observation, and this is your Newtonian gravity. So this is one of the discrepancies, and this is observed both in clusters, galaxy clusters. So people like Wood, Zwicky, they made this kind of observations. You can also look at it in the galaxy also, and that was done by Vera Rubin and many other people. So, and the cluster and the galaxy, they correspond to different scales, because the clusters is basically a combination of many galaxies. So it is much bigger in size compared to a galaxy. So, but you see this thing in both the scales, at the scale of cluster as well as the scale of galaxy also. And another way of thinking about is this, that your galaxy has some kind of spin. It's actually moving around its own axis, and it is spinning so fast that if you take only the visible mass of the galaxy into account, you will not be able to balance the centrifugal force with the gravitational force. So that is another way to think that if all the stars are actually bound together inside a galaxy, the galaxy should have more mass compared to what you see by counting only the visible matter or the visible stars. So that is one point. Another point here is that why this velocity or the rotation curves, so these are called rotation curves. So why these rotation curves remains flat at high distances is because this fall is coming because you have already assumed that the mass of the galaxy is confined only to the visible radius. There is no mass beyond it. But if you now assume there is some mass beyond it, then what will happen is that the mass will also increase with r, and that will try to balance the fall in the velocity if you go by this formula here. So then what will happen is the mass is also increasing, and this r, so if the mass is also increasing linearly with r, then what will happen is that this r and this r square, that will give you 1 by r. Then 1 by r is on the left side also, that will cancel out. So ultimately we'll see that v is actually proportional. V actually remains constant if you go to large distances. So that actually led to the hypothesis that there should be more mass in the galaxy or even in the clusters, such that the velocities remain more or less constant if you go to uh, high values of, or large values of r. Similarly, you can have other things also. So for example, I mentioned that this similar observation you can see in the cluster as well. And then there are observations like gravitational lensing, bullet cluster. So the lensing is something like what you see in optics. So if you have a lens, you know that your light gets kind of bent, like a focus to a particular point, depending on the type of the lens and the position of the object in front of the in front of the lens and so on. Similarly, if you have a very massive object like a star, and if your light is coming from the background and you are here with a telescope like this, the light can come like this and can actually bend. So what you will see some kind of virtual image here for this object. And this is a unique prediction of the Einstein's theory of general relativity, and this has been already experimentally verified. So this this lensing phenomena can also give rise to some evidence of dark matter. For example, if you are here and you are looking at some kind of galaxy, so let us say this is a galaxy somewhere, and you are looking from here, and there's no visible matter here, so you will see the galaxy as its original shape, and we know the shapes of galaxy like a spiral or some other kind of galaxies. But if there is something in the foreground which you do not see in your optical telescopes, but what it can do is that it can actually bend the light coming from here. And if they bend the light coming from here, the images of these things will be actually distorted. So they lead to some kind of distorted images of this cluster or the galaxy, which is not what you expect to see. So those kind of indirect things also tells you, and the amount of lensing or the distortion in the images will tell you how much of mass is contained in the foreground. So that tells you that there should be way much more matter compared to what we see in case of um, in the optical telescopes. So these are the evidences at the galactic scale or the cluster scales. But even if you go to even larger scales, much larger scales, like the size of the whole universe, so there also we find evidences, and those evidences come in the form of cosmic microwave background. So you might have heard about cosmic microwave background, CMB. So CMBs are basically the photons which are coming from around 380,000 years after the Big Bang. Uh, so at that time, what happens is that the protons and electrons, they combine to form hydrogen, and after that, the universe became charge neutral. So TCMB is of the order of 380,000 years. And we live in a universe which is the T now is 14 billion years, right? So this, when the proton and electron combine to form hydrogen, the universe became charge neutral, and whatever photons were there, they are just free streaming from that epoch to right now. So that corresponds to a temperature of the order of 3000 Kelvin. The temperature right now is around 2.73 Kelvin. So what do you mean by temperature? So by temperature, I mean that if these photons, they are like a blackbody radiation, and we know from our uh, physics knowledge that the blackbody radiation or the blackbody spectrum corresponds to a particular temperature. So these photons behave like a blackbody spectrum, and when they were emitted at the recombination time or the TCMB time, they correspond to a blackbody temperature of 3000 Kelvin. But these photons have been traveling for a long time, so they will lose their energy because the distance between the photons and us is actually increasing, because we live in a universe which is actually expanding with time according to the Hubble law. So that actually lead the photon to lose their energy. And right now, these photons have correspond to blackbody spectrum of 2.73 Kelvin, and their wavelengths are also getting redshifted because the space between the source and the detector. Detector is basically us. We are seeing the background photons which were coming from such a long period, 380,000 years to 14 billion years. So if the space between the two points, the source and the detector, is actually expanding, it's very similar to like a Doppler effect, which we already know. This will actually lead to the increase in the wavelength. So even though they were emitted in the ultraviolet, right now we'll be seeing them in the microwave. Okay, so that's why they are called cosmic microwave background. So this cosmic microwave background, this actually tells you a snapshot of the universe when it was as young as 380,000 years. Okay, and from that we can actually get some evidence for dark matter. So what it calculates the photons. It actually tries to find out the photons coming from all directions in the sky. And you might have seen some kind of CMB maps which looked like this. When they project the whole sky map into a two-dimensional paper, it actually looks like this. So you will see that there are some colored dots like blue and red and so on and so forth. All the CMB map looks like this. So blue means slightly colder temperature, and the red means slightly higher temperature. That means they are black body, but all the photons, they actually do not have exactly same temperature. So there's some kind of small temperature fluctuation. So delta T by T is of the order of 10 to the power minus 5. So this is very small kind of fluctuations. That is the difference between the temperature of the blue dot from the red dots. But there's small fluctuations, but they are non-zero. That is very important. So what you can calculate is that you can find out this some kind of correlation functions between the two photons coming from two different directions, and try to find out how these correlation functions look like if you vary these correlations over different theta or different angles in the sky. So they give rise to some kind of angular correlation plots, which is, so this is CL and this is L. L is basically your spherical harmonics. That's the one you use in the hydrogen atom, for example, in quantum mechanics. So this actually looks like something like this. Something like this. So this height and the position of this peaks actually tells you what kind of universe we live in. That means we live in a specially flat universe. That is told by the position of the first peak, and the relative size of this first peak and the second peak. It actually tells you like how much of matter we have, how much of dark matter we have, and so on and so forth. So I will not go into the details because this requires some more cosmology stuff. So I am just telling whatever minimum cosmology we need to understand these evidences. So this tells you, so the pie chart I told you earlier, that we know that our present universe has around 26% or 27% kind of dark matter. So how do we know this? Because CMB measures the universe when it was as young as this, and it actually measures everything that was there in that universe, and then they try to extrapolate from 380,000 years to 14 billion years, assuming that your model or the universe is actually governed by a model called lambda CDM model. So lambda is basically cosmological constant. CDM means cold dark matter. So we live in a universe which has a lambda, which is cosmological constant, that gives you dark energy, and CDM means the cold dark matter. So when they extrapolate it, they find that the present universe has 27% dark matter. When the cosmological constant when the CMB was emitted at 380,000 years, at that time the universe did not have 27% dark matter. It was much. It was. It has to be slightly more, because at that time the cosmological constant was not uh, dominating the universe. So, but at that time we had more radiation also. So if you look at the present universe, we have 27% matter and around 5% ordinary matter or baryons like protons, neutrons, and mostly hydrogens and some amount of helium. All other elements you can ignore completely from the cosmological point of view. Radiation content in the present universe is even small, like 10 to the power, so that we can find out how much of these photons contribute to the total energy budget of the present universe. So that will be the radiation. It gives you 10 to the power minus 5, which is very small compared to the matter and the dark energy. So this is one thing. Then the CMB is one, and the other is the structure formation. So we live in a universe which has structures. That means we see the formations of galaxies, clusters, and so on and so forth. How do they form? If you are familiar with the well-known cosmological model, so what we propose is that we live in a homogeneous and isotropic universe. on large scales. That means on the size of the visible radius of the universe. That means everything is distributed more or less uh, homogeneously and isotropically. But if we look at the local universe, we find that there are structures here, but there is some void, empty void here. So that means things definitely do not look homogeneous and isotropic. So what has happened is that from a very homogeneous and isotropic fluid in the very early universe, the universe has evolved into a one which is at small scales look very, very anisotropic and very, very inhomogeneous. So how these things have happened? So these things have happened because there is dark matter in the universe. So what dark matter does, so why it is called cold dark matter? It is called cold dark matter because cold means heavy or non-relativistic. It can mean heavy or non-relativistic compared to the usual visible matter. So what will happen is that, and it is cold because they interact mostly through gravitational interactions. So dark matter, they have gravity, definitely gravity, because all the evidences I have told about, they are rely on gravitational interactions only, but it can have very weak interactions also. Gravity is already the weakest force, but you can have slightly stronger than gravity, but much weaker than the other known forces like the electroweak or the strong forces. Okay, can have very weak interactions also. So if we assume these things about the dark matter, so what it will tell you, the dark matter does not move very fast or does not interact very fast with other guys. So they will just remain non-relativistic. They will not feel the other forces much strongly, and they will not move very fast like other guys. Uh, you can just think about if we have a positive charge and if you bring a negative charge, since they feel each other's Coulomb interactions, they will move very fast, right? But if you assume now that they do not have electromagnetic interaction, they have only gravitational interactions, you can find out that the velocity, and you'll find that they will be very small because gravitational force is much small compared to the electromagnetic force. So, so the cold dark matter means they will behave like a non-relativistic kind of matter, and they will form in the universe. What they will do is that since they are non-relativistic, so in the universe you can assume that if there is some initial, some very small deviation from the homogeneous and isotropy universe in the early stages, because that is actually shown by the CMB, because CMB tells you that there is something called delta T by T 10 to the power minus 5. So there you can assume that there will be some regions where you have some over density. That means delta rho by rho is non-zero. Okay. There will be some regions where you have some kind of over density in the early universe. And if you have over density, what will happen is that because over densities will have some kind of gravitational interaction. So if you are seeing a photon coming from this over dense region, because photon will also feel the gravity, because that is how the lensing thing also occurs, as I mentioned earlier. So the photon coming from this over dense region, they will appear to have some less energy because they have already lost energy by climbing against the gravitational force, which is imparted by this over dense region. So they will give rise to those blue dots in the CMB because they correspond to slightly lower energy. On the other hand, if you are coming from the underdense regions, those photons will have maximum energy because they are not climbing against any gravitational interactions. So they will correspond to the red ones. So this is what CMB tells us. So now, if we have some initial inhomogeneities, so what will happen is that the dark matter will also the feel the gravitational potential of this, so the dark matter will go there. So these regions will be mostly occupied by dark matter. Why not other matter? Because the other matters are moving very fast because they have all the electromagnetic interactions and all other strong interactions and weak interactions and so on, and they are also light. So they will keep moving and interacting like a random walk type of scenario. So the dark matter will go here and they will form clumps. Okay, all these things will grow because there is dark matter. They could not have grown if there is no dark matter. Okay, so they will grow, they will become bigger and bigger. So ultimately, what will happen is as the universe becomes colder and colder, that means the universe has expanded, and if you expand the universe, temperature goes down. So then what will happen is that slowly the other matter, the visible matter, will also lose their energy, and they would also start feeling the gravitational potential of these local overdense regions formed mostly by dark matter. So they will fall there. So the baryons will also fall there, and then what will happen is that you will see the formation of stars to begin with. So that's how the first stars will form, and then you will have the combination of stars which will form galaxies, and then we'll have the formation of the uh, clusters and so on and so forth. So that's why the present theory of structure formation tells us that we live in some kind of halo of dark matter, and there the galaxies are formed like this. Okay, so because the baryons fall into the dark matter over dense regions to form structures. So this is like some kind of dark matter halo, which is all around us. So all these things tell us that we live in a universe which has dark matter. And the interesting thing is that the evidences are coming from experiments or observations at different scales, from kiloparsec level in the say Milky Way to say hundreds of kiloparsec in a cluster, and to hundreds of megaparsec at the level of cosmology. So these independent measurements across different length scales actually convincingly tell us that there is some matter. We know it matter because matter contributes in a specific way to the expansion of the universe, and also matter contributes in a specific way to the structure formation, which I have just mentioned. So we definitely know that dark matter behaves like a matter. So what do we mean by matter quantitatively? When I say matter, it means its equation of state. That means your pressure is actually zero. So pressure is actually related to the energy density by some parameter called rho, which is called the equation of state parameter. And omega is zero for matter. Okay, so they behave like a pressureless dust, so that's why I call them non-relativistic. And the presently, whatever this matter that we talk about, the visible matter, they also have omega equal to zero, because right now, as I mentioned, the temperature is the 2.73 Kelvin. So if you convert it to electron volt, they'll be milli electron volt. So the temperature right now is of the order of milli electron volt. And all the particles that we have in the standard model, they have mass of all standard model particles except photon, obviously. They are much more compared to this milli electron volt. And this is the usual definition when we use to distinguish between relativistic and non-relativistic particle. That means if mass is much more compared to the kinetic energy, it means the particle is non-relativistic. If mass is much less compared to the energy or the kinetic energy of the particle, that means the particle is relativistic. So right now, both dark matter as well as ordinary matter behaves like pressureless matter with omega equal to zero. But if you go to very early universe, when the temperature was much large, so the kinetic energy or the thermal energy, which is Boltzmann constant multiplied by temperature, will be much more compared to the rest mass of different particles that we have in the standard model. They will all behave like a radiation. So that's why when you talk about Big Bang and all these things in the present universe, you can think of it starts with something like a radiation, and then it convert into matter, and then now we have slowly getting dominated by dark energy. And this is very easy to understand because radiation energy density goes down as 1 by length to the power 4. Matter energy density goes as 1 by length cube. Dark energy is very special in the sense that its dark energy remains constant energy density, and that's why it is called cosmological constant. So if you start in a early stage of the universe where you have radiation dominated, so if you go back, so this is the say time or the say size of the universe, or say size of the universe. So if you start with a radiation dominated universe, let us say your energy density rho radiation, this is your rho, it will fall very fast. So this is your radiation. there was less matter at the beginning, but it will fall slightly slower. So you can think that at some point matter will take over. On the other hand, if you look at this cosmological constant, which remains constant, okay, so this will just remain like this. Okay, so this is your matter. So at the Big Bang, we have radiation dominated, or like here, but radiation is falling very fast. At some point, matter will take over. So this happens around, say, 50 or say 70,000 years after the Big Bang. And lately, what is happening is that the matter is falling and falling. So here, the dark energy starts to take over. And that happens around, say, maybe 8 billion years. And now we are here, which is 14 billion years. Okay, so that's why we see that around 68% of the present universe is dominated by dark energy, but we still have some amount of dark matter in the ordinary matter. But if we go very far into the future, we can clearly think that if the present model, which is called lambda CDM model, is still valid, we expect to see more and more dark energy in the future compared to the matter, because they will just behave like this, okay, in this simple model. All right, so this is about the evidence that we have for dark matter. Now, the question is that what can give rise to dark matter? Now, you can, because you know that the ordinary matter is composed of fundamental particles. So if you also believe that or assume that dark matter is also in the form of some kind of particle, then it has to satisfy certain criteria, that it has to be electromagnetically or color neutral. Because why? Because I have already mentioned that they do not interact with light, because that's why we do not see them in the optical telescopes. They do not emit light, so that's why they are electromagnetically neutral. They are color neutral also, because I mentioned that all the evidences are based on gravitational interactions, but they can have some other interactions also, but that has to be much weaker compared to the standard model interaction. So they cannot have color, because color means they have strong interaction. They would have been seen in the experiments, so they are not seen in any experiment. So, and second one is that they have to be stable, because as I said, the dark matter has played a non-trivial role from the time when the structures were forming, because it acts like a seed to the structure formation, and it is also here in the present universe. So that means it is there in the universe for almost the entire duration of the lifetime of the universe. So it has to be very stable or long-lived, right? And other criteria, you can say that, okay, it has to agree with all the experimental constraints, like whatever you have seen. It should give rise to 26% or 27% in the present universe, and so on and so forth. So it has to obey all limits. Now, if you assume that the dark matter is also like a particle, what kind of particle can be dark matter? So the easiest or the first guess everyone will have is that can neutrinos be dark matter? It's a very good choice because it is electromagnetically neutral. It doesn't have any color or strong interaction. It is stable because neutrinos are the lightest fermion that we have in the standard model. So it cannot decay to anything else. It satisfies more or less. But neutrinos have other issues. For example, one can calculate how many neutrinos are there in the present universe. So one can calculate this very easily, because neutrinos, so this part you can look at the book called Early Universe. First three, four chapters. This is by Colben Turner. A very useful book to understand cosmology and its connection to particle physics. So one can calculate the number density of neutrinos as well as any relativistic part, because neutrinos remain relativistic for a long duration in the universe. So the relativistic particles number density goes as T cube. And this is just statistical mechanics. So if you know the distribution function, you use Fermi-Dirac distribution or Bose-Einstein, you just integrate over the phase, over the momentum, and the volume, and you'll get the number. And if you just divide by the volume, then you will get the uh, number density. And if you ignore the chemical potential and all other things, if you assume that the mass is not playing any role, so the particles are relativistic, you will find that number density goes as T cube. And I told you that the present universe, the T is milli electron volt. So that means I can calculate what is the number density of neutrino. It will come out to be 335 neutrinos per centimeter cube. That means in the present universe, there are 335 neutrinos per centimeter cube of volume. Okay, and these neutrinos are primordial neutrinos. They are not coming from sun, earth, or any other things. They're just there from the beginning of the universe. And they have very low energy, that's why. All the other neutrinos, for example, the neutrinos from the sun, they have energy of the order of mega electron volt. The neutrinos from the atmosphere, they have energy of the order of giga electron volt. So they have different energies. But these neutrinos are very cold because they are coming from a long distance. And the mass, we know that the mass of neutrino is sub-electron volt. So one can calculate what is energy density of neutrino. And you will find that this will come out to be less than 5.6 into 10 to the power minus 32 gram per centimeter cube. And if you calculate, because I told you that pie chart, so the pie chart tells you the relative percentage. So those percentages are calculated in comparison to something called critical density. So those they are called omega. So this is omega means rho by rho critical, and rho critical is the critical density, which is tells you 2 into 10 to the power minus 29 gram per centimeter cube. In the expression wise, this is just 3 multiplied by the Hubble constant at present divided by 8 pi g. G is the Newton constant, and Hubble constant is right now is around 68 kilometer per second per megaparsec. So what does it tell you? It tells you that if two galaxies are separated by a distance of say 1 megaparsec in the present universe, they are going away from each other by a speed of 68 kilometer per second. So this is just coming from the Hubble law, which tells you that the velocities of two objects separated by a distance d is just v is equal to h naught multiplied by d. But they will go away from each other only when they are separated by a scale of say 100 megaparsec or so, or cosmological scales. Sun is not going away from us, or even the Andromeda is coming towards us. Okay, so locally they are not. This law is not valid. This law is valid only at very large scales of the order of when d is say more than 100 megaparsec, like 10 to 100 megaparsec. Anyway, so this is a little digression for those who do not have not learned or read anything about cosmology. So this omega neutrino you can find out, and this will come out to be, because you can find out, you can put these values here, g Newton constant, you can find out that rho critical is this, rho neutrino I have already found out. So if you find out omega neutrino, you will find that this will be less than 10 to the power minus 3, which is much less compared to omega dm. Because omega dm, as I told you, this is 0.27, 27% in the present universe. Okay, so this is one criteria that so neutrinos cannot give rise to dark matter, because neutrino energy density in the present universe is way too small compared to dark matter. Any other point? Another point comes from the phase space argument. For example, that tells you that the fermion dark matter, because neutrino is a fermion, so fermion dark matter mass should be more than order 1 kilo electron volt, and that comes from something called phase space argument, and that is called the Tremaine gun bound. So this just tells you that the galaxy has a particular phase space, and it cannot exceed the phase space of a degenerate Fermi gas. So you know what mass of a galaxy should be coming from dark matter. So if it is coming from a fermion, if the fermion mass is lighter than a certain bound, that means you have to put more and more fermions to accommodate for the mass that is contained in the form of dark matter in that particular galaxy. So if the fermions are very light, that means you have to put too many fermions there, and that will exceed the upper limit that is coming from the available phase space. It is just coming from the fact that you cannot have two fermions in the same quantum state, right? This is the Pauli exclusion principle, basically. So that tells you that if at all neutrinos have to give rise to dark matter, its mass has to be more than kilo electron volt. But we know that neutrinos are sub-electron volt, so it cannot give you. The third nail in the coffin is basically that neutrinos are relativistic always. Not now, because now the temperature is milli electron volt, but mass is like 0.1 electron volt. So neutrinos you can think of as non-relativistic right now, except the lightest one, which can be massless as well. But mostly neutrinos are relativistic. And if neutrinos are relativistic, they will not form those clumps to act like a seed of structure formation. They will always keep moving at a high velocity without trying to come together and form some kind of clumpy structure. So you cannot do that. Okay, so that means it actually tells you, I hope it actually convinces you that none of the particles, neutrinos were probably the closest one, but neutrino also fails to give you the dark matter. So that means you have to talk about some new particles. So we need, that tells you that we need BSM to explain dark matter. Okay, so now what kind of BSM you can have any particle. For example, you talk about a scalar particle, they can have a scalar, say phi. It can have another fermion, say psi. You can have some boson, B mu, which are all different particles. So once you introduce a new particle in your theory, you have to you have to first write down what kind of interactions it has. Okay, because if you assume that this particle has only gravitational interactions, then it is very hard to explain how, because I mean that is also a viable possibility. But the problem is that if you assume that the dark matter has only gravitational interaction, it is often hard to tell you how this dark matter was produced in the early universe. Because in the early universe, we know that the other particles are produced because they have interactions like electromagnetic interactions, strong interactions, and all other interactions. So they can be produced one from the another and like scattering, decay, and so on and so forth. But if dark matter has only gravitational interactions, it is so weak that you will not be able to produce it. You may not be able to produce it in sufficient amount. So usually when we write down a dark matter model, we first propose what kind of particle it has, and it should be, and then we try to write down a Lagrangian. So now let us write down a very simple dark matter Lagrangian. For example, let us say our dark matter is a scalar, and let us say our dark matter is a singlet scalar. Then it is even easier. So that means if I choose phi, which is a scalar particle, to be dark matter, I assume the phi to be a singlet. So first identify the quantum number of the phi under SU3, SU2, and U1. So I already mentioned that the dark matter cannot have color, so that means it will be singlet. It could be doublet under SU2, but for the moment I'm assuming it as a singlet under SU2 also. And U1Y, if I put U1Y non-zero number, then it will also gain an electromagnetic charge. And I also already mentioned that because I already know that the electromagnetic charge is coming from T3 plus Y by 2, right? This is the formula that you already know. So if I put U1 Y non-zero and T3 is anyway 0 because this is singlet, it will give you a charge. So I'll put Y 0. So this is just a singlet. What kind of interactions it can have? It can definitely have, so this is a real scalar singlet, let us say. So the Lagrangian of this dark matter, I will have half the Klein-Gordon Lagrangian. This is the kinetic term. It will have a mass because dark matter has to be massive. I cannot have a massless scalar. I need to have a massive scalar. Okay, what else it can have? These are all self interactions. One is the kinetic energy and one is the mass term, and also you can have lambda phi 4, right? I can write phi cube also, but I'm not writing it for the moment. I'm just writing this kind of quadratic and quartic terms. Can it interact with the standard model? What kind of terms it can write in the standard? This is a perfect singlet. Can it couple to the leptons? It cannot couple to the leptons because leptons are doublets. Can it couple to the right-handed leptons? But right-handed leptons are singlets, but they have hypercharge, so you cannot couple to them also. Can it couple to the Higgs? Yes, because Higgs, you can write it like this. For example, you can write lambda phi Higgs. You can write down H dagger H. H dagger H is already a standard model singlet because you write m square H dagger H for the mass term. So this is already a singlet. You can add a term like phi square. Okay, so you can write this term. Now, why I am not writing the terms which are, say, trilinear or like linear? In principle, if we have only this symmetry, I could write terms like this also, phi Higgs dagger Higgs, with some kind of dimension full term. I'm not writing that. Why I'm not writing that? Because it will lead to phi decay. It will lead to phi. If you write down the Feynman diagram for this process, it will lead to phi going to 2x. Okay, so I don't want to do that. So that means it will lead to phi decay. That means phi is unstable. And I already told you one criteria that dark matter has to be stable. So that's why in often all these models, one not only introduce a new particle, but they also introduce a new symmetry under which the dark matter is stable. Because you cannot put a charge of this particle under the standard model, so you put a new symmetry. So let us say I have a G2 symmetry. So the G2 symmetry is a reflection symmetry under which the particle, under which the x goes to minus x. So if I say that my phi is odd under this G2, that means I can write only phi square or phi 4 terms, because then minus 1, if this is minus 1 square, minus 1 4, all these give rise to 1. That means your final Lagrangian is Z2 even. So your Lagrangian has to be Z2 even. That means it has to be plus 1 under G2, just like the Lagrangian is invariant under all other symmetries like SU3, SU2, E1. It has to be invariant under G2. That means it has to be G2 plus 1. Okay, so that means if you write this term, for example, this is Z2 minus 1. You cannot write this term. If you assume that your Lagrangian is invariant, invariant means under a G2 transformation, this term should remain this term. But you know that phi will go to minus phi if under this G2 symmetry. That means this term under G2 will become minus mu phi h dagger h. That means your Lagrangian has get a new sign change. So that means this term is not allowed. But if you write phi square Higgs square term, this term will remain same because phi will go to minus phi, but phi square will go to phi square. Okay, so that means if you have a G2 symmetry, you can forbid all these terms which are linear or like trilinear in phi, and that will actually prevent the dark matter of phi to actually decay into the standard model particles, and that actually agrees with the fact that the dark matter is actually stable. So if you do that, now you can actually do the rest of the analysis. Like you can, because now you can think that okay, phi will be produced from the from the Higgs interaction. So one can have two different types of interactions. Say, let us say this phi Higgs 6. So you can have phi Higgs 6 interactions. You can also have phi coming. It can go through a Higgs because Higgs will get a vacuum expectation value. So after electrostatic symmetry breaking, you can have a trilinear vertex also, phi Higgs, and this can go to all standard model because Higgs couples to all standard model like the fermions and the gauge bosons. So you can have phi to standard model interactions through the Higgs. Phi to Higgs is already there. So you can produce phi, and you can actually find out what will be the abundance of this phi in the universe. Okay, so to solve it, to actually find out the abundance of phi in the universe, one has to first know the thing like whether the the phi was actually thermally produced in the early universe, or it was non-thermally produced. So if it is thermally produced, that means it can be produced in equilibrium. That means phi phi to Higgs Higgs, or phi phi to Standard Model, all these interactions are in equilibrium. So when you say equilibrium, for example, phi phi to Standard Model, this process, the rate of this process, let's say this is called gamma, is the rate. This is this was above the Hubble, which is H is the Hubble. Okay. Because the rate at which these two phis are coming and produce two standard model guys is more than the rate at which the universe is expanding. So that means this process was in equilibrium. So if this process was in equilibrium, then one can calculate the dark matter Rayleigh, which is called the typical WIMP type of dark matter. And there one has to solve the Boltzmann equation. Boltzmann equation is not very difficult to find, so one can find out this Boltzmann equation is basically tells you how to calculate the number density of a particle which is not in equilibrium. So it was initially in equilibrium, but what is happening is that the rate of any interactions will actually go down with time because the temperature is cooling down when the universe is actually expanding. So when it falls down, then phi will go out of equilibrium. So if phi goes out of equilibrium, you cannot use the Fermi-Dirac or Bose-Einstein distribution to calculate its number density. So then one has to solve the Boltzmann equation. So the Boltzmann equation is very simple. So this is for example n phi. This tells you the rate of change in the number density of phi with time plus 3h n phi. So this 3h and phi, what does it tell you? So this h is basically Hubble. So h is basically a dot by a. So a is something called the scale factor. That means your universe, the volume of the universe, you can think of is as proportional to a cube. A is the size of the universe you can think of. So this term, if you put this equal to 0, what this will tell you, this just tells you the very simple thing which you already know, that n phi goes as a to the power minus 3. If you write h as a dot by a, then integrate this equation, you will find that n phi goes as a cube. That means the number density of a matter particle going as 1 by volume, which we already know. There's nothing new. But now this right hand side is not exactly 0 because it has the other processes. So this, for example, there will be processes. If the particle is neither created nor destroyed, just remains same, then it will go as just like this. But I know that there are some interactions because we have already written down the Lagrangian, where we have written phi phi to Higgs Higgs and phi phi to standard model interactions. So that means there are some kind of processes which is making sure that your standard model is producing your phi. Okay, because this is going to increase the number of particles. But there are some processes where your phi is also going to standard model. You just take the forward process phi to Higgs 6 and the backward process. And when these two processes are in equilibrium, that means gamma Sm to phi and gamma phi to Sm, they are in equilibrium. So they will be equal and hence they will become 0. So that means in that case, the number density will just fall as 1 by volume, which we already know. But as I mentioned, that these processes will go out of equilibrium at some point. And if they go out of equilibrium, you cannot say that the forward and the backward processes are happening at the same rate. So then one has to actually put these things, and that will give you. So these are rates. So rate, I'm sure you have learned about cross sections in the cross section in your quantum field theory and the standard model. So what is cross section? So cross section can be related to the rate. Cross section is basically the rate of a rate divided by number of target multiplied by the beam flux. That is the rate at which the particle is going in a particular direction from the target divided by number of targets and the incoming beam flux. Okay, so one can find out the rate, that is what is coming into the Boltzmann equation, which is gamma is equal to sigma, which is cross section, multiplied by the number of targets, which is n phi volume, and multiplied by the beam flux, which is n phi V relativity, V relative velocity between two phi's. Two phi's are coming. So for a phi, the phi is the targets. Okay, so phi is coming, hitting another phi and going to standard model. So n phi multiplied by volume, because it is number density and v is the volume. So that is giving you the number of targets. That is how many number of phi's are there. And number density of phi multiplied by the relative velocity tells you the beam flux, because beam flux is number of particles divided by per unit area per unit time. So this V is meter per second, and this is particle divided by volume. So this gives you number of particle per unit area per unit time. Okay. So this, if I use in the Boltzmann equation, so I will get I will get dn phi by dt, the usual term, which is already there. I can write this as sigma v n phi square minus n phi equilibrium square. Okay, so what does it tell you? That means if phi is in equilibrium, so if phi is in equilibrium, then n phi is, if phi is in equilibrium, then n phi is n phi equilibrium. Okay, then this becomes zero. So if this becomes zero, then we actually get back to the earlier result where n phi goes as 1 by volume. But if n phi is not in equilibrium, we get it like this. So this is also we are getting, because we wrote this to be SM going to this phi minus phi going to SM. So this also we can find out just by because this is SM to phi. This will be because these are standard model particles which are already in equilibrium. So this process is actually same as the rate of equilibrium going to SM to phi. On the other hand, this one is not necessarily in equilibrium because phi is not in equilibrium. And we know from the principle of detail balance that in equilibrium, SM to phi is same as phi to SM. Okay, and I have already mentioned that I can write down rate as n square. This is the V is the volume. So rate per unit volume, gamma divided by volume, I can write as n square sigma V relative. So if I put this back here, I can write down this one as equilibrium, and this equilibrium I can write as equilibrium phi to Sn. So the equilibrium Sm to phi I can write as equilibrium phi to Sn. So that's why this one I can write as n phi equilibrium is coming square, because I have already mentioned that I can write down the gamma by volume as n squared. Okay, so that's why it become n phi square, which is equilibrium, and minus sign is coming because here it was plus sign. Here this is plus, so this is minus, so that's why this minus is coming, because I have put extra minus sign here. So I will get this equation by assuming that the processes involved are just 2 to 2 processes, like 2 phi going to 2 SM and 2 SM is going to 2 phi. Very simple processes, and that we have already realized how to do it in phi case, because I have phi to SM and SM to phi. So if I write this process equation, I can actually solve this Boltzmann equation, which is not very difficult. You can write down this sigma as some. So the sigma is the cross section. You know how to write down cross section for phi to. For example, if I write phi to Higgs 6 processes, it's not very difficult. So phi to Higgs. So this is say lambda. So this cross section will be proportional to lambda square divided by m phi square. There will be some more factors coming from the phase space and all these integrations of the matrix element squared. I'm ignoring it, but dimensionally it will grow as this. So if you put it back here, you will find out that if you increase lambda, what will happen that the cross section will be more because the coupling is more. So you will find, if you plot how this number density will behave as cross section, you will find that instead of writing number density, I can plot NA cube, which is the number, and we'll find that this number remains like this, and it actually falls, and then it becomes like this. Okay, so if you have so this is like the equilibrium one. And here what is happening is that there will be some kind of e to the power minus m by t kind of suppression, because as I told you that the number density is a cube, t cube only when the particle is relativistic, but as the temperature is going down, the particle mass will become important at some points, and then you will have this extra factor like e to the power minus m by t, which is coming from the Boltzmann suppression in the distribution function. So then it will slightly decrease, and when it goes completely out of equilibrium, at this point what is happening is that your rate of phi to SM is actually falling below the Hubble. So this will actually start departing from the equilibrium line, and it will actually become flat. Why it become flat? Because now we are talking about numbers now. That means universe is expanding. So this can be some kind say A. So the universe is expanding, of course, but the particle is neither created nor destroyed, because phi to SM has gone out of equilibrium. SM to phi, although SM is in equilibrium, but SM energy is now less compared to the mass of the particle, and that you can always see, because here I have already assumed, you have already seen that the temperature is becoming less compared to the mass of the particle. And all the standard model guys have energy of the size of the temperature, because it is just the Boltzmann constant multiplied by the temperature. So the standard model particles are already lighter compared to, say, dark matter. So they cannot annihilate into the dark matter number, because they do not have enough kinetic energy as well, because temperature is already less compared to dark matter mass. So why they are getting flat? Because neither dark matter is going into standard model, because that has already fallen below equilibrium, nor standard model is going into the dark matter. And hence, its number density will fall, but number will remain same. And when this happens when it goes out of equilibrium. So if your lambda is more, if you're more lambda, so the lambda will increase in this direction, or the cross section. If you have more cross section, then what will happen is that the dark matter will get annihilated more, because it will keep going into standard model more and more. So that means it will leave a lesser and less abundance. So this is how we actually calculate this kind of dark matter abundance. But since I do not have time, I have talked about only one type of dark matter kind of production, which is called the WIM. And this is one of the very popular dark matter candidates, because it can have sizable interactions with the standard model. And one interesting thing about WIMP is that it not only gives rise to 27% in the present universe, but you can actually test this idea in different experiments. For example, if you think about, because I have these Higgs to phi interactions, okay, and the same will be true for any other candidate also which you take. Now what will happen? Now if you have some kind of experiment, for example, you have this Large Hadron Collider. Large Hadron Collider, you already know that you have this protons, and the protons will be coming, and let's say protons will come and form the Higgs by the gluon fusion or something else, and the Higgs can go into all other standard model particles, plus it can also go to phi now, if phi mass is slightly less compared to the Higgs mass divided by 2. So, and the phi is stable. So, and phi doesn't have any standard model interactions. Like, it doesn't have any color, it doesn't have any electromagnetic. So what it will look like? It will look like some kind of missing energy, because the detector will not be able to detect it. So when you conserve the energy momentum, you will find that, okay, some of the energies looks like you are not being able to conserve with all other particles that you have detected in your detector, because obviously phi will carry some momentum. So they should look like some kind of missing energy signatures in your collider experiment. Let us look at delay detection experiment. So what is delay detection experiment? Because you can have some kind of detector, large detector, where we can have some kind of xenon, argon, or whatever, and you expect that the dark matter particle will come, because we live in a dark matter halo, as I mentioned, and our solar system or our galaxy is our galaxy is actually moving in the local cluster that we have, and hence we know that we expect to get some kind of dark matter particle passing through us, Earth, or any detector almost every second. Okay, so if a dark matter particle comes, if you have some kind of nucleus, and the nucleus has some, say, quarks or say nucleons, and nucleons will have quarks, and the quarks have Higgs interactions. So you can have something like a phi coming and phi outgoing, and this is a Higgs have quark interaction. So what it will do, the phi will coming with some kind of velocity, say 10 to the power minus 3. It will come, and it has some mass. It has mass much more than, for example, compared to the nucleon, because phi is very heavy, like let's say 100 GeV or so. Nucleons have mass only, say, 1 GeV. So what it will do, it has some kinetic energy as well, so it will actually give you some kind of recoil. So if you can measure that recoil in your delay detection experiments, it can actually eject some, if the nucleus is getting recoiled by this dark matter, it can eject out some of the electrons, for example, and the electrons, because you can put an electric field here, like an anode and the cathode, and then the electrons will get accelerated towards the positive charge. In that process, it can emit some kind of photons, which you will see in your detectors, and from that you'll be able to find out what was the recoil energy imparted by the dark matter particle to your nucleon, and that will tell you what should be the mass of the dark matter particle and what is the rate of interaction of the dark matter particle with the Standard Model guys. So far we have not seen. So what these experiments actually put, they put some kind of lower bound on the some kind of upper bound on the dark matter nucleon interaction, sigma cross section, as a function of dark matter mass, and we find that we get some kind of bound. So this is, say, LZ 2023, and this is coming at very precise now at the order than a minus 48 centimeters square. On the other hand, if you look at typical weak interactions, they are of the order of 10 to the minus 35 or 34. Okay, so this is way small, but it is pretty amazing that the dark matter experiments have been able to go down up to this level, like ruling out dark matter nucleon cross section up to a level of 10 to the power minus 48 centimeters square. And this happens for a particular mass, like around 40 GeV or so. So this idea is actually testable, and one can test it in different ways. But of course, this is not the only dark matter candidate. There can be many other dark matter candidates. Since I do not have time, I talked only about the scalar dark matter. You can have fermion dark matter also. For example, I talked about type 1 CISO. So you can also ask the question that, okay, you have this right-handed neutrino. So we add 3 different types of right-handed neutrinos, 1, 2, and 3. But to explain solar and atmospheric, you need only 2 of them, because you have 2 masses effectively. Because I told you that the lightest neutrino mass can be 0 also. So you can have two guys to explain the solar and atmospheric, and the third one you can have a dark matter also. But then you have to be careful, because now they do not have any other symmetry. Okay, so that means this nu R1, let us say nu R1 is your dark matter, so nu R1 will still couple to this. Okay, so what you have to ensure is that nu R is sufficiently light. That means it cannot decay into Higgs and neutrinos, because Higgs is 125, so you can say that, okay, nu R is very light, but it can still decay at one loop. Okay, because you can always have, say, nu R, and after the symmetry breaking, your nu R actually mixes with nu L, so it's mixing. And since nu L has interaction with electron and W, you can have electron and a W and a nu L, and you can have some kind of photon emitted from either this leg or this leg. So nu R can decay into a photon and a light neutrino. So that actually puts more bound on this Yukawas and the mass. So one can actually satisfy this whole thing if your Yukawa is very, very small. So in this case, so this is one example where dark matter is not like a thermal dark matter, because this Yukawa has to be very, very small. So it is something like a non-thermal dark matter. And and it's also very light. It is not like a GeV scale, which I mentioned in the case of scalar dark matter. So this has to be much less compared to the electron mass. Otherwise, it will decay to electrons, like a 3 electrons. So these neutrinos, if it is has to be dark matter, mu r dark matter, then it has to be less than MeV. And there are strong bounds from some kind of X-rays and gamma ray experiments, even if you satisfy all other quantities. So basically, the thing is that we do not usually, when you write down models, I mean, you don't have to write a model to fit everything. But for example, I write down a model for neutrino mass. I can always try to see whether that same model can explain the dark matter or not. So for example, the type 1 CISO is a very simplest example. And I did not have time to talk about the matter-antimatter asymmetry. So it turns out that the type 1 CISO can also explain matter-antimatter asymmetry, can also explain dark matter, also, although for a very small range of masses and coupling, you can explain dark matter. And you can also explain neutrino mass. But all these models have different advantages as well as disadvantages. So for example, type 1 CISO, you can say that, okay, it's very minimal model. You just have 3 particles added to the standard model. It is giving you neutrino mass, it is giving you dark matter, it is giving you leptogenesis. But this model, one drawback of this model is that it is very hard to test this model, because these newars, either they are very heavy, or they are, even if you make them very light, they couple very feebly to the standard model guys. So it is very difficult to produce them in any experiment. And like I mentioned, like you have the detection experiments, but the detection experiments will not see these kind of particles, because this kind of dark matter do not couple to the um, uh, do not give you this kind of tree-level dark matter nucleon or dark matter electron scattering. But it is a very minimal model, so it is difficult to test this model unless you have some more ingredients. So this is how we do this kind of model building in any BSM physics. It depends on which problem you want to solve. And it's also not about solving a problem, because solving a problem, like you can solve a problem like all the problems that I mentioned in 1,000 different ways. But then one has to also answer the question that, okay, how can I test this model? Because ultimately you have to test your model in some experiment. So if you do not find a way to test your model, then your model is, it's not, it's in a way good for nothing, in a sense. So you not only have to fit your model with whatever we observe, but you also have to predict like what kind of new things you can see in the experiments, such that your model can be tested. Otherwise, this field will not move forward, because you will just end up writing thousands of models, but you will never be able to test, or you have no idea how to test those models. So yeah, so I will probably end here. So I hope I could convince you like how to what are the model, what are the drawbacks of a standard model, which actually motivate us to write new models, and how to write a model for say neutrino, how to write a model for dark matter, how to write a model for both, for example, and how to test those models. I hope I could give you some preliminary idea about this stuff, and yeah, if you have any questions, I'll be happy to take.
Thank you, Devasisda.
Mhm.
So we can take some questions if you have any questions. Anyone?
Participants, if you have any question, please unmute yourself. I'm sure they have lots of questions, probably hesitating, or maybe they are very tired.
Yeah, it's already the end of the school, so.
Yes.
Yeah, I'd like to inform the participant that Dr. Devasis Bora, he is right now in US, and he has He's taking your classes from there. So at this time. So you can.
Yeah, sir actually started at 3 a.m. I think. So
Yes. So it's very difficult for him to manage the time. So you should at least respect it and have your doubt cleared.
No, it's okay. I think their doubts are cleared already. So
okay, so there are
Anyone?
no questions. Oh, there is a question in the chat box. Sir, can these dark matter particles form objects? Okay.
yeah, that depends on the model actually. Uh, you can hear me, right?
Yes, yes.
Yeah, I mean they can form structures. I mean, I mean now the question is like what kind of object you are talking about. If you're talking about structures, of course they can form that they have to form. But if you think about like whether they can form objects like the quarks form nucleons or nucleons form nucleus, can they form these kind of very tiny bound states? That depends on the model. For example, the scalar singlet model or the neutrino, right in the neutrino dark matter model that I mentioned, they cannot form any small bound states like the nucleon or the atom because they do not have any other they do not have any strong interaction. So if you have some kind of strong interactions among the dark matter, because what I said is that dark matter should not have strong interactions with the standard model. That's why they do not have color. But if you assume that dark matter also has some kind of strong interactions among themselves, and it has a much rich structure, not just one particle, but can be many particles which have their own interactions, just like standard model has many particles, then you can think of like dark atoms or dark nucleons or something like that. So there are models where people study those scenarios. Because they can have some other advantages, but they are certainly very non-minimal. But yeah, all dark matters have to form structures on large scales. So that is a common property of all cold dark matter candidates. But whether they can form these very tiny objects like atoms, nucleons, that depends on the model. That is not generic. No, I'm not doing postdoctoral. I'm too old to be a postdoc. I'm on a sabbatical.
Okay. That was the nice question.
So if there are no further questions, shall we move to the regulatory session? Also, there is a
Yeah.
question. There is a question by Rajkumar.
What is the
If
question?
if DM have interactions with gravity, is it necessary to construct a Lagrangian including gravity counterparts?
That is usually not required because if dark matter has gravity, it will satisfy. You can do everything using Einstein's relativity as well, just like classical gravity. But at the Lagrangian level, you may have to write when you talk about how this dark matter was produced. So people, of course, we do not have a quantum theory of gravity, but one can write some kind of semi-classical type of interactions with graviton and dark matter particle. And the graviton couples to standard model also. So one can write those kind of interactions. And the graviton you have to write as a two-index tensor because we know that it is a spin-two object. So one can write down those interactions. People have tried to study those things for very heavy dark matter, which can be produced through some kind of graviton-mediated processes. But for the structure formation and all the cosmology, the classical general relativity by Einstein is more than enough.
Okay. So I hope that answers your question, Rajkumar. So shall we then move to the validatory session?
Yes, yes, yes. We can.
Okay, okay, okay. Uh,
Okay, nice.
Okay, so let's move to the valedictory session. So we had finished our school today. I hope the participants were highly benefited from this school. They could learn lots of new things. Probably they have although we had to cover lots of topics within a short span of time, but I'm sure because of the instructors, we really did justice with the topics. And we would like to hear some feedbacks from the participants. You can unmute yourself so that if we organize such events in the future,
So the
it would
recorded
be.
lectures won't be deleted, right?
Yeah, recorded lectures will provide. I mean, you already have the access to the recorded lectures, no? So we'll maybe provide you in some platform, in some website of PANE or something like that. So you can always access to these lectures.
Okay, sir. Okay.
Mhm. So yeah, participants
We are
will,
planning
it
to
would be very
put all the
helpful.
lectures in our YouTube channel. So once we do that, we can share this to you.
Okay.
Sir,
Yes.
sir,
Yes,
I
Deep.
had a small suggestion that maybe 1 hour lectures will be better than like almost 1.5 hours of lectures, because these topics are a little tough. So I feel we would feel more refreshed if it was 1 hour lecture with a smaller gap than what is given right now. But and so on.
Mhm. Yeah, I think that is possible. This time we planned it for a short span of time. Therefore, we had to go for 1 hour and 30 minutes plus. But yes, that's a good suggestion. Probably we can think of. Yeah, after 1 hour, sometimes it becomes difficult to be attentive for every minute. So, anyone else? Any comments, suggestion, feedback?
We can think of 1 hour, but there are topics which actually require more than 1 hour, unless
That
otherwise
is correct.
continuity is broken many of the times. So maybe we can have a mix of 1 hour and 1.5 hours. So in our next school, we can think about that.
Probably we can have very small breaks, say 5 minutes or 10-minute break, and then continue.
Possible. Yeah.
We can think. Okay. So actually, it would be nice if we can organize something offline, and uh, because in online platform there are many disadvantages. So let's see. Also, can winter school on similar topics be organized by PANE? Maybe offline too. I think Samradha, you'd like to answer that question?
Yes, we are thinking about a winter school also, but winter school will not be on the same topic because PANE has to cover many topics. So this winter school will possibly be on, I think, astrophysics. Let us see. Any
Okay,
other
so
suggestion for our next school so that we can also improve? Any constructive suggestion from anyone else?
Hello, sir.
yes, Sagnik.
Yeah, sir, I think there could be some like a brainstorming session or discussion sessions in place of some tutorial session so that students can interact, or there will be some group discussion. It will help students to interact and discuss these topics in place of some tutorial sessions.
We can do that. Yeah.
Actually, tutorials are supposed to be like a brainstorming session, but since we have to do it online, like that is the disadvantage. So we did tutorials as if we are doing the class. So tutorial should be interactive. So yeah, we can probably think of a better way to conduct these classes.
Yes, maybe what we can do that, we can actually keep no tutors for some tutorial classes and let the participants discuss among themselves. That we can do. I think this is a good suggestion. So we can keep some tutorials without any tutor.
Yes, sir.
If you
Exactly
recall
what I.
the SCRC schools, the participants are asked to come to the board and solve problems. So if the participants want that, that also is one option.
So for online session, I was thinking that just the way you said, like if a question is given and we are given like 5 to 10 minutes for us to attempt solving that. After that, either the professor telling the solution or one of us, telling the solution. After that, we'll have more discussion, because without attempting, if we're already getting the answers, I think that kind of uh, limits the doubts we could have.
Yeah. Yeah, that is one way.
Yeah. Actually, we can also do. We can actually share the questions one day.
Sir, I wanted to ask about the need of mathematics in theoretical
Should be the thing.
physics. As soon as we enter physics major, it is complete onslaught of physics knowledge with less focus on mathematical insights into it. Okay. So anyone would like to answer that? I wanted to ask about the need of mathematics in theoretical physics. Probably sir can answer that.
No, I mean, there's no alternative. So, I mean, I think all theoretical physics or any physics undergrad or the postgraduate curriculum, they go through intense mathematical physics courses, and also like pure mathematics course also in undergrad 101, 102. So I think the training is already provided, unless you are coming from, say, engineering background or something else. So I think whatever is provided in the curriculum is good enough. I don't think anything else is required. No need to stress too much. Whatever curriculum is giving you in 4 year plus 2 year programs and also in PhD courses, that is good enough. So you don't have to run ahead of time. You just go through whatever is provided at your level slowly with patience, working out everything on your own. I think that is good enough.
Okay. So Devasatita, would you like to give the formal vote of thanks? Probably we can also
Yeah.
have a photo session because that is required. So
Yes.
yeah.
So we should have a session. Yes. So
Shall I
online
have
photo
the photo
session.
session first, or then the vote of thanks would be better, no?
Yes. Let's click the photo first.
Okay, okay. So we'll request everyone to switch on their cameras. So we'll have a photo session. Yeah. Take the shot. Okay. So a few more participants, please. Okay.
So I think Debabrot, you can click.
Yeah. Yeah, yeah. Yeah, one is done. Let me take another. Yeah, it's done. Thank you, everyone. So I would like Devasatita to formally give the formal vote of thanks. And
Yeah. So Thank you, Devabrat. So today is the last day of this summer school. We are actually very happy that this school be organized, and our participants have attended most of the lectures. And first of all, I'd like to thank all the speakers who actually agreed to give their talks in the very first approach. And you can see starting from Prabal, Subhada, then Satyasati, then Debasista, and Subhadya. Yeah. So all of them have given their
Tirtha.
lectures. And TikTok, yes, yes, TikTok. So everyone has done their part very well, and starting from the very basics, actually starting from QFT, which is one of the basic tools for theoretical physics. So Prabal Fukan has completed 8 lectures with tutorial. So he rigorously done the things, and then I'd like to thank him actually. So even he was really very busy with his university work, and he was very loaded, but even after that also he never said no, that I cannot do, or he did everything. He prepared each and every notes for you every night, sitting till midnight. So it was really, he's really means I have no words to say thanks to him actually. So the way he has supported us, and Subhoda, he's always with us. He helped us to get other people connected, like Soibyo and Tirtho. So he has contacted them for us, and agreed to give the talks. And you could see how the group theory classes were taken by Soibyo and then Tirtho. All the classes were actually excellent classes. And today Devashish, he is sitting with you from US at this time. Now it is, I think, morning there. So uh, so no word to say thank you to the speakers, but thank you to all of them, and to all the participants for joining us from different parts of India as well as abroad. And I hope you have got lots of benefit from these lectures. Even if you could not attend the class, you could at least go through the videos and notes that we have provided to you. And I'm sure the way these teachers, these instructors have gone through the courses, so you will rarely find these things in your college or university classes. And so finally, thank you, Robert, so for uh, um, helping me in all the ways. Actually, I am just in the namesake for the namesake. Actually, he was doing everything starting from the very first day, and that thanks goes to you. And Samrat is also here. Samrat has he has supported us from in all aspects. So thank you everyone. And Samrat is there. I'd like to say request Samrat to say a few words. Yeah. Yeah, let me use there was connection. I'm sitting with him actually. Yes, thank you very much all the participants. It has been a fruitful summer school, and it is possible only because of your participation in large numbers. Thank you so much. And lastly, I would like to thank Dr. Devabrat and Dr. Devajyoti, the two conveners. I have seen them working and planning everything so meticulously. Without their, of course, this Pane Summer School wouldn't have been possible. This is the first Pane Summer School, in fact, the first school of Pane, and there will be many more to come, but it will be a historical one because it is the first one. Thank you so much. And your certificates will be delivered in your email. Certificates you will receive within a couple of weeks. Thank you.
Yeah, I just want to mention one thing, that this school was planned with Dr. Samrat De. So one day we were just having a casual discussion over a cup of tea, that can we do something under like this under the banner of Pane. So actually the idea originated from that discussion. So I'd like to thank Dr. Samrat De. And I must appreciate the effort given by Devasutita and particularly Shubhaditya Bhattacharya sir. He was, I mean, helping us in every aspect in organizing the school. So yeah, I thank every participant, all the instructors, and also I forgot to mention, we should not forget about Niloy and Indrasit for providing us the tutorials. So that were really helpful despite of their busy schedule on their own research.
And Pritam,
So yeah, Pritam, he also gave a lecture last day. Yeah. So on that note, I think it's a good point to stop. We'll provide the certificate on due time. It will be sent to your email IDs. Okay. Okay then. See you.
Okay, bye bye.
Yeah. Bye.
Thank you, sir.